Okay. Okay, so I'm going to go through just the process of how we did the reader error through my two populations. So just as Eric was saying, kind of as an overall theme that we noticed as we moved south with our populations, the error tended to increase. We aren't entirely sure why. We think it has to do with the temperature differential and just how they grow experiencing warmer temperatures. So it's an area of future research for us. So for my data, we broke it down into 30% subsamples. For Kathleen's data, she only did about 20% subsamples, and that was in reference to a paper on reader error that she found. But because we expected higher error rates for New Jersey, for my animals, we decided to do 30%. For us, we did males and females separated just to keep my data the same kind of throughout the process. And I attempted to make my subsamples out of the highest quality images that I had. So here is a pretty decent image of an older animal. This one's at least 200 years old. And here's an example of a bad image. So specifically, when you look at this corner right here, it might be a little bit harder for you guys to see it, but it's entirely blurred out and you can't see half of the lateral edge. So right in this section here for people on Zoom. So we wanted to avoid these because these are going to increase our error and bias issues kind of no matter what. So Sarah, Pace, and I aged each of these subsamples, and it was the same for Kathleen. Once I got her results back, and we aged the same ones, aged the same animals. Once I got her results back, I ran this through the code that was generated in R by Kat and Eric Robillard, and we followed those same exact tests, the McNamara, Evans-Honig, and Bowker tests. We also did coefficient of variation as well. So for bias tests, of course, we were looking to see is someone aging too high or too low from the other person. And basically, we wanted to make sure that these p-values were not statistically significant, so greater than 0.05, because that would indicate that there is no bias. And at the same time, we also measured the coefficient of variation for precision, and if a singular animal had a CV greater than 10%, those were taken from the subsample, and we would age them together to figure out why our error was so high for that shell. And that was termed consensus aging. So whenever it was Sarah and I together, or there were times where it was all four of us, me, Alyssa, Kat, and Sarah, all in one room, and we were sitting there and aging one shell together, we would figure out, again, as Eric was saying, where those areas in the shell were that were the most difficult. Like if there was one kind of pattern, like we saw in that shell that we aged, that big black band with like 7 small lines in it. So that's where we answered those questions of, do we age all of those lines or just the thickest and most dominant? So after we had those consensus age meetings, I would then go and generate another 30% subsample, and I would send those back to Sarah. And thankfully, by round 2, usually our numbers would be appropriate. So we would have not statistically significant bias, our CVs would be lower, and our binomial test would indicate that our error overall for the population was lower. So the thing with error for New Jersey, because they grow a little bit differently, especially compared to Georgia's Bank, as we'll see a little bit later in our presentations, is that there are just a lot more check lines. And because of that, there's just higher error, because for a lot of those check lines, we don't know whether or not they're true annuli. And so we tend to mark them anyway, or we won't mark them anyway, kind of depending on the reader. So that's going to boost our error up no matter what. So unfortunately for us in New Jersey, my error was a little bit higher, especially compared to Kathleen's Georgia's Bank. So mine was over 10%. I think it got about to 12 to 13%, but we found we couldn't really get it much lower than that. So that's what we went with. So we did some side tests, and Eric talked about this, but for those younger animals, we looked at our subsamples. We saw that we had very high CVs with animals that were less than about 50 years old. We pulled those from the subsamples, reran just the older animals through the code, and we found that our error had dropped significantly by more than 10% in some cases. So it went from like 20% all the way down to like 9 or 10. And again, that's just because a lot of those younger animals have increased check marks. We're not sure, again, if they're true annuli. Some will always age them, some people won't always age them. We still did have some bias, but we did see that the younger animals were the true, or like a huge cause of a lot of our error in these instances. We also double checked the same thing with males, because we were often seeing that males do have higher error rates, but just to also kind of just check ourselves for consistency's sake, we took 50 shells that we had previously aged, completely renamed them so that we weren't sure whether or not they were male or female or what sample they were, and we aged them again. We compared them to the old age, and males were much harder to age consistently than females were. Again, we're not sure if, males do grow a little bit differently compared to females, as we'll see a little bit later on, but they were a little bit harder to age maybe females effectively. So again, females, we recommend sticking with females when you're aging quahogs. Any questions?
Did you have any males aging males?
No. All female.
Well, I guess, well, I guess we did have Roger, so,
Yeah.
but that's it. All of us ladies, we know what we're doing, but.
We don't have any questions in the chat or anything.
Nope.
Okay. So there is a paper out in Journal of Shellfish Research, Kathleen's first author, dealing with the precision and bias issue. It's a much more detailed evaluation than what you've heard today. So if you want to burrow into this problem, that's where you should go. And if I can send you the reference. Okay. So you look at this, and of course we were worried about this too, because we worked very hard to get the precision problem or the reader error problem down to a tractable amount. And then of course the question becomes, are we still getting the right answer? Because maybe we are now aging all of our ocean quahogs precisely, but they're all too young, they're all too old, right? So what's the solution there? And that's a job for Alyssa to talk about.
Okay. Let me pull up my presentation real quick. Okay. So when we were trying to determine whether or not these ocean quahog ages are actually accurate, not just precise, we decided to use radiocarbon ages. So this is calibrating radiocarbon ages of ocean quahogs. So just back to that terms of reference, reader accuracy, we evaluate the interpretation of radiocarbon dates as a mechanism to evaluate reader accuracy, including the correction factor for marine reservoir effects. So when we age bivalves like ocean quahogs, radiocarbon dates are often used to evaluate the accuracy of an age reader. But these ages need to be calibrated. So how do you calibrate these? So radiocarbon results need to be calibrated to account for changes in atmospheric concentrations of carbon-14 over time. And so to do this, we have a calibration curve, which compensates for the fluctuations in atmospheric C14 concentrations. And so we'll use calibration curves such as intercal or intercal 20. So that's great for atmospheric carbon. However, there's a different concentration of radiocarbon in the atmosphere versus the ocean.
Let me break in very quickly. The IntCal 20 is not something we've done. This is a national
This is
effort by everybody using C14 to come up with the proper atmospheric calibration for those evaluations. So there's a huge body of literature behind that, and everybody in the world probably uses that.
it's
Certainly
the
everybody in
global.
US. So but I wanted to make sure you didn't think that this is something we invented.
No.
This is something that the C14 folks have been, working on since they started using C14.
So what Eric was just saying for everyone on Zoom is this whole INC Cal calibration curve. This is a global curve that's used. We didn't come up with that. This is just what everyone who does radiocarbon ages references.
And one other thing while I'm thinking about it, because you might scratch your head about this, where does the C14 come from? Because C14 decays, right? It's an isotope. It's a beta emitter, and it's got a half-life of, what is it, 5,000 years or something. Okay, in that neighborhood. So, you would think by now all the C14 would be gone. The reason why it's not gone is it's created by cosmic rays hitting the atmosphere. So there's a mechanism that continuously creates C14. And if man didn't fool around with it, that would generate an atmospheric equilibrium value of C14, because there's a continual addition process and removal process by the decay of the isotope. So it gets to an equilibrium condition. The problem, of course, is that man does fool around with it, and that's a story I'm sure Alyssa will talk about in a little bit. But prior to man's ability to fool around with it, the general atmospheric calibration number was always true.
And so what Eric was talking about there with the interference of man, that's the atomic bomb. So we have this calibration for time, and then we have the atomic bomb, which messes up a lot of the calibrations. And so you have to, yes. So after early 1950s, there's a whole nother way to calculate everything. So to be able to calibrate marine samples, we have to have a marine specific calibration curve. And so these differences between the ocean and the air are primarily caused by the rate of exchange between the air and then the ocean's surface, as well as the circulation of the carbon through the ocean and just local physical factors. So we need to account for the spatial differences in the marine environment, as well as the changes through time. And so in order to do this, we have the local and temporal differences calculated as the marine reservoir age. And so we need to be able to calculate the marine reservoir age in whatever location that you take your marine reservoir samples. So present day marine reservoir ages range from anywhere from 400 years to 1,000 years near the poles. So to describe the variation in marine reservoir age between regions, we consider how the marine reservoir age at a particular location varies from the globally averaged mixed layer reservoir age. And we come up with this equation down here. And we have the regional correction of marine reservoir effects as reported by this delta value.
I'm going to break in again. You think that ocean and water ought to be quote unquote the same age, but actually the ocean circulation is, in particularly deep water circulation, is much slower than the rate at which C14 decays. And the only way you get C14 into the ocean is at the surface, because you're exchanging C14 across the ocean atmosphere interface. So there's a rate at which C14 is put in there. And once that body of water leaves the surface, it doesn't get any more C14. So it's sitting there decaying away, and the water gets older and older and older. And the question is, here's our little clam sitting there on the bottom, and how old is the water that goes into the clam? Now, there's an interesting thing about bivalves that is really important here. And that is that more than 90% of the carbon that's in the shell is taken from CO2 that's dissolved in the water. Okay. In other words, you know, when you eat something, you're eating a bunch of carbon compounds. And when the clam eats something, it eats a bunch of carbon compounds, and it breaks those things down, and it respires CO2 just like we do. And if that was the primary source of carbon in the shell, then you would need to know what the carbon content was of the food in order to figure all this out. But by the grace of God, bivalves don't use that carbon to any extent to make the shell. They pull the carbon for the shell directly out of the water. So the age of the shell carbon is the same age as the water carbon in which it was made. Wasn't for that, you couldn't use C14. So that's really kind of a miraculous thing actually to say. Now, the issue that you've got in the North Atlantic, I hope I'm not stealing your thunder. Am I?
That's the next slide.
Okay, I won't say anything more then. I will stop.
Yes, so to follow Eric's train of thought, right here, I'm just going to go over the equation real quick. So you have the global average that's been come up by other scientists who've done a lot of work with C14. And then to be able to determine the local marine reservoir age, you have to have the difference between the two, and then you have the local marine reservoir age. So all of our samples are from the Northwest Atlantic Ocean, where there's an absence of studies to find that marine reservoir age. So that makes it a lot harder to actually calibrate our radiocarbon samples. So we can take all these radiocarbon samples, but to actually get an accurate age, we have to figure out the right way to calibrate them and determine a marine reservoir age for the area of our samples. So we're thinking the marine reservoir age is at a lot greater depths or higher latitude, or sorry, a lot of the marine reservoir ages that have been calculated in the North Atlantic are at greater depths or higher latitudes with mixes of water from different sources from the cold pool. And so that's why we need to estimate the marine reservoir age for the cold pool where all our samples are. So our objective is to determine the marine reservoir age for the North Atlantic that best fits the North Atlantic, and then use a comparison between the birth years of ocean quahogs collected from Georges Bank, Long Island, and New Jersey, and then compare that to the radiocarbon ages and the calibration that we think is best fit. So this is just a quick review of the sampling process. So I'm just going to review how we actually get the carbon samples after we do the whole aging process. We, actually get the shells, we go through the processing, then we age them. I take a carbon sample from the earliest part of growth on the hinge, and then we send that off to UC Irvine, and then they send us their marine or their carbon dates. And then that's when we have to calibrate them. And so we used a bunch of different values, and we found the best fit marine reservoir age was actually 400 years. So I'm going to skip ahead to this. So we used all of these shells that Kat and Jill visually aged, and these were all the shells that we sampled, and we compared them to the calibrated C14 birth years, where we used a calibration of 400 years, and those were the ones that were best fit and had these residuals that you see in this plot right here. So based off of that, we were able to find that there was a mean deviation of 7 years, or sorry, it was a mean of 7 years off of the calibrated ages and a standard deviation of 4 years. So the comparison of the birth years obtained by directly aging the shells to the radiocarbon ages.
Let me chime in
Okay.
again, okay? So the radiocarbon people have gone through a number of major efforts to come up with the overall average age of ocean water. And there was one, quite a number of them. One of the very important ones was in 2013. There's been another one in 2020. The results of Marine 13, which is what it's called, was that the average age of ocean water was about 400 years, plus or minus a little bit. Now, the water is older at the poles than it is in the tropics. It's older in the deep water than it is at the surface. If you think about the cold pool where ocean quahogs are living, that water is primarily ultimately coming from the Labrador Sea and the Erminger Sea. It flows down through the Gulf of Maine and around George's Bank and filters in along Long Island and slowly replenishes the cold pool south of Hudson Canyon. It is a variable mixture then of surface water, which is put into it while it's mixing its way along the coast, the Labrador Sea water that's coming down, and additional cold waters that are coming down from the area around Greenland and Iceland, for example, that get entrained. So, and that degree of variability changes from year to year. If you look at the European literature, you will find significant papers where they have attempted to evaluate the degree of variability associated with the reservoir age in comparison to what fraction of the water has come from various water masses to create the water that exists, for example, in the North Sea or the Norwegian Sea. Okay. A lot of effort in Europe about this. So there's uncertainty built into the reservoir age. And some of that is corrected by this delta R that you just saw in that equation, which is the local deviation from the overall world average. So if the overall world average is 400 years, somewhere the deviation may be 20 years, in which case you would use 380 or 420. Okay. If you go into the estuaries, just as a warning, okay, estuaries don't work this way. And that's because there's a lot of old carbon in estuaries because the rivers are dissolving limestone. And limestone is C14 dead. And so the amount of carbon, dead carbon coming into the estuaries is highly variable based on the river flows and the watersheds. The consequence of that is, if you ask the question, where is all the reservoir measurement work been done in our area of the world? It's almost 100% focused on oysters and hard clams because people are trying to come up with the local reservoir deviation in the Chesapeake Bay and the Delaware Bay and Long Island Sound. Okay, that's where all the work is. You go offshore, and there is not a single measurement between George's Bank and the North Carolina border on the continental shelf, except for what you just saw on the screen.
Yeah.
Keep talking.
So we were able to fit that 400-year correction. So we just stuck with the global average, and that's what fit the best with all of our ages. But obviously we have this issue when we're trying to see if our ages are accurate with C14. And then we're also using our C14 calibration or our ages to see if our C14 calibration is accurate. So you have this idea of circularity introduced into the literature that is kind of redundant and doesn't really give you an exact.
And this is where I blow my horn, okay? It's really interesting. Every single marine reservoir age in the North Atlantic, including all of the work done in Europe, every single one of them comes from Arctica. And the presumption is that the Arctica ages are correct, and therefore the reservoir deviation that you measure when you measure the C14 content of the shell is a direct measurement of the local reservoir effect for that area where the ocean quahog came from. All of the measurements. Okay. But then if you look at the European literature, for example, and ask the question, how do they prove that they're accurate in their ages? Every single one of those comes from comparing the C14 value to their age, right? So the quahog made the reservoir effect, and the reservoir effect made the quahog. Everything, you know, there's not a single data point in the northern Atlantic that's different from that. So of course we've been just as circular. The nice thing about this is, and our argument about accuracy is, that even with all this circularity, we come out with a data set that's effectively on the overall ocean average reservoir effect of 400 years, which happens to be the correction factor that essentially everybody uses outside of estuaries and really deep sea. Okay, so either the world is wrong or not, because we agree with the world. But I would really strongly suggest, you know, if you're ever talking to your NSF scientists and people about this, someone needs to come up with an independent reservoir effect measurement that does not involve ocean quahogs for the Northern Atlantic. I mean, one number would be kind of nice.
Some other isotope that you can pinpoint, like the explosion of
No, the bomb problem is a huge problem. Are you going to talk about the bomb thing? No.
It was like this side.
So the atmospheric testing was in the early 1950s. It put an enormous pulse of C14 in the atmosphere. It took an extended period of time for it to work its way into the ocean. So you see C14 beginning to rise in the ocean late 50s and early 60s. Then we stopped testing atmospherically. And at that point, that carbon began to decay. And it also began to continually mix into the deep water of the ocean, because of course, before that, it wasn't there, right? And so you see this skewed parabolic curve, okay? And you can attempt to use that to date animals that were born post 1950. There are papers published. There's a very nice one for the either the Gulf of Maine or the Labrador Sea. Collada, where was he? He's one of those two places.
Mm-hmm.
A very nice one that's something in our neck of the woods anyway, in the sense that it's on our side of the Atlantic, in which he worked out the post-1950 delta C14 values for that region. That may or may not be valid for our region because it's much further north. But there's basically, once you get post 1950, you know, it's one of those things that you need to just, you know, either you're going to spend a lot of money or you're not going to know. Prior to 1950, the other answer to your question is there are other isotopes that can be used back in time, uranium isotopes, for example, but they're not good for more recent values. You know, if you're worried about the last glaciation in the Pleistocene or the early Holocene or something like that. Now, there's something called amino acid racemization, and that's used a lot. What's that about? All amino acids in proteins that, for example, you carry around with yourselves are the left isomer. Okay. When the protein degrades and the amino acids are released over a period of time at a known rate, the L isomer will convert to the D isomer. And so the LD ratio can be used to track time. Aspartic acid is particularly good at this because it converts pretty fast. The problem with amino acid racemization is, unlike C14, the rate function is temperature dependent. So you've got to know the temperature. And the second piece of this is it's got to be calibrated. And 100% of the time, well, no, that's not true. From time to time, it's been calibrated against museum shells. And you know when those animals were collected. But the vast majority of calibrations use C14 to calibrate the rate. Okay, so now you're back to the C14 problem again, right? So it's cheaper. You can do more animals, but you don't get over that little problem. So the key thing would be to get shells of a known death date from a known location, do C14 on those to get you the local reservoir number, which then in comparison to the world average would give you the local correction factor. Okay. And of course, in order to do that, you got to go back and find let us say an Arctica that somebody happened to have on his shelf in the middle 1700s. And they're, where are you going to find that? So this is a real sticky wicket. And the only thing that we can say is that the numbers that we have are very supportive of the 400-year value. And the 400-year value is very supportive of the numbers we have. And if it had come out any other way, we would have been disturbed. But this would appear to us to mean that with all of this reader error business that you've heard about, on the average, the signal is pretty good that we're coming up with reasonably accurate age estimate. It's whatever else you need to say.
That you covered a lot of it. I think that's good. Biggest thing, like you said, is the circularity.
Questions about C14 on the chat? Is there anything? I don't know. No?
It seems like you could get, with a little patience and some lab time, you could know that you were accurate for young. Quantum.
Yeah. That's correct. So Dan said, with a little patience and financing, you could know that you're accurate for young animals because you could raise them, right? Now, in fact, we know that they can be raised because Roger did that when he was up at Huey. So that's something that we know. We also know that you can do mark recapture and you can show that a single band is true. There are good methods now that weren't available in the ropes era to stain carbonate while animals are alive, so that you can come back later on and know how much time has passed from the line and the shell. Tetracycline has been used. There are some other dyes that have been used, and they're all effective. They've been used for bivalves, for corals. You know, it's a very well determined technique now. So if you had the time, you could go back and do the Murawski study, and that is to pull up a hell of a lot of ocean quahogs, stain them all, throw them back overboard, and come back some years later and pick them up and find them. The fact that he was able to do that, because I've done this mark recapture stuff, the fact that he was able to do that off of Long Island, I consider to be one of the real miracles. Because that it's, I mean, if you think about it, what's the chance that I throw this animal in the water in, 50 meters, and I come back a few years later and I pick it up, And so that's a hell of a study. And you could do that now with thousands instead of tens, if you wanted to. So the technique, I mean, it's a good question, because it's feasible now to contemplate doing that, and over a fairly wide area. But it's not inexpensive. Yeah. So nobody's done C14 on surf clams, and the reason why is that you need a living surf clam that was born before 1950. Which, alas. Now, I talked to Roger about this, because there are a lot of museum collections in which probably some animals were collected at least in the early 1900s and maybe in the late 1800s. And but it's a destructive procedure. So you'd have to tell them, I'm taking the clam that a doll collected in 1880, and you're never going to see it again. The museum folks don't tend to like that. Well, where are the shells? No. You're right. In the 1980s or late 70s, okay, there would have probably been some animals collected that were pre-bomb. But I don't believe, and I asked Roger about this, because John Ropes kept everything. I can't believe that there's not a collection of Ropes surf clams, because he did all of the surveys off the Chesapeake in the early days of the fishery. And I've asked Roger, where, if you were going to look for rope shells, where would you look? Because I think it would be worth the hunt. That's the one thing it would be really a big deal if we could find a collection of his shells that he collected in the late 1950s or early 1960s off the Chesapeake. Well, why don't you go up there and see when they were collected? Yeah, you need the shells. Yeah. I mean, it's worth a look, because that would be the places where you might luckily find some animals that are pre-1950. And then that would be a good way to look at the reservoir effect, at least for the very shallow ones, inner shelf. Do we need to plan lunch?
Probably. But Roger had something to say, and Nina did raise her hand at one point if Nina wants to ask her question.
Oh, is this up here? Here's Roger's response, Dan. if the rope shells exist, they're somewhere in your infamous warehouse.
Yeah, I was gonna just look and see when the first date samples we had. What year that. I'm guessing we at least kept the hinges. I don't know. So,
Yeah, you'd have to grind up the hinges. And Nina had a comment?
Yeah, hi, this is Nina Whitney from Hui. Sorry I can't be there. I guess my comment is that I'm not convinced that the reservoir calculations are as circular as you're suggesting, Eric, because we use radiocarbon to get a sense for when those clams are living, but then we cross date them. So they are independently dated before we do a reservoir calculation. So the reservoir calculation is calculated based on comparing their cross-dated age, which is using techniques from the dendrochronology world, what the tree ring people do, and then comparing that to their radiocarbon age and the difference is the reservoir age. So I don't think it's quite as circular as you're suggesting. I mean, cross-dating is a pretty robust technique for dating these clams.
Yeah, so I'll agree with that. The problem is none of those come from our neck of the woods.
True. There is one in the Gulf of Maine, but yeah, not as far south as you. Yeah.
So there's the Gulf of Maine, and there's some early work by Weidman from George's Bank that had an 018 time series associated with it, in which he tried to extract the bomb carbon signal out, I think, if I remember right. So that, there's spotty work here and there, but we don't have anything local.
Well, we are working on it. We are cross-dating, well, as you know,
Yes.
collected clams from there. We are cross-dating them and there will be radiocarbon ages associated
So
with that.
Nina is on this new NSF grant, okay? And she's the 018 person. She does cross dating, and she was out on the pursuit cruise. We sent back at least one and maybe two freezer fulls of shells.
Yep.
So in the hopes that NSF was going to bless us, which they did. So yeah, so we're looking forward to her shedding light on this murkiness. Okay, did we decide about lunch? People in virtual land, you don't have this problem, but are we going to do lunch? Are we going to order? Or what are we going to do? Any ideas?
yeah, are you looking to order something?
Well, we can't go out. It takes too long to come back. So if we could, can people handle pizza? Is it okay? What we need to do is send a victim to a pizza place. Or unless there's one that delivers. I don't know if they do. So Teresa's going to work on this while we talk. Yeah.
Yeah, or at least a vegetable. Huh? White pizza?
Yeah.
You can have a
I like white pizza.
White pizza, vegetable pizza.
White-
Like a broccoli.
white
or-
clam
Oh,
pizza?
broccoli would be good.
White clam pizza?
No, plants. Yeah.
Yeah, you're.
I do like them. Do you
I
want
can
anything on your
remember the plant
pizza?
pizza.
Anything on the white pizza? I don't know if I would eat. I mean, what it has.
Yeah, yeah,
Like
I would eat some
vegetable.
white pizza.
broccoli or mushrooms.
Yeah, mushroom.
with red beans.
Broccoli or something.
No tomatoes. No, anything else?
Yeah.
Yeah, no tomatoes.
Okay.
Vegetable like pizza.
And then, should I get to one of those?
Yeah, probably.
And then how many pepperoni pieces?
Was this the next one?
One cheese, one pepperoni.
Yes, we do.
Move it up.
Yes, I'm just bringing mine up too.
Oh, okay.
No.
Yeah, yeah. Yeah, it's a Census bill, so just save the receipt. I don't know how much it's gonna cost. They need 20s, I got them.
Make sure you get napkins too, lots of napkins. If they have plates on them. Okay. So now you're on for AJ.
Okay, so next item on the agenda. So having confirmed that we think we know what we're doing about aging these animals, the next thing to do is to come up with an age length key so we can apply that to a length frequency in the field and come up with the age frequency, okay? And so I'm going to start out with Kathleen's work on George's Bank and Long Island. So in a nutshell, here's the problem. There are over 200 age classes in Arctica. You know, age length keys is for a given length, what the probability is of age, right? So if I have an 80-year-old clam, some of them, you know, are 50 years old, some of them are 60 years old, some of them are 70 years old. I have to know what the proportion is for the animal that's 80 millimeters, okay? And it turns out in Arctica, there are a lot of potential ages. The age length data are highly variable. You're going to see this, the reason for this as we go through this meeting. But at a certain size, growth slows considerably, but animals live for a long time. So if I take a 5 millimeter size class, okay, I could easily have 150 different age classes in that. Which means if I'm going to know what the age length relationship is in that 5 millimeter thing, I really should age at least 150 animals, and probably more than that just for that 5 millimeter class. Okay, that's really the problem that exists in Arctica. Okay, so the question is, what can we do, and how good are we at doing it? Samples. We went to sea on the Pursuit in 2015. These were the samples that gave us Sarah Pace's papers, and we got length frequencies for 2 sites based on almost about 3,000 animals at each site. And then in 2017, we went back and we collected some animals at these sites for aging. And in between these 2 dates, we discovered, to our dismay, that males and females don't grow at the same rate. And you'll see information about this later on. So we decided that, you know, this could have a big impact on age length keys. And so we were going to have to sex a whole bunch of animals. So we got 706 animals from George's Bank. We opened every one of them on the Pursuit and sexed them and brought them back. Long Island, over 1,700, of which 904 were aged. So 615 were aged in George's Bank, 904 from Long Island. You'll see in a little bit, we did the same thing for 2 sites in New Jersey. And at this point moving forward, all of the analysis were sex-based, based on the fact that we didn't know if we had to do it or not, but we knew if we didn't do it, we were going to have to do it. So we better do it. Okay. Now, the question is, how did we do this? And just very briefly, you go through the aging process, right? So you know the size of the animal, you know its age, you have a bunch of, and you divide them into 5-millimeter bins, and you have males and females, okay? And then you ask the question, how reliable are these age length keys, okay? And the standard approach, we built some software to do this. The standard approach is to take an age length relationship from one of the sexes, let's say it's the male one, and generate an age frequency, and then take that same male age length key and apply it independently to the female age frequency or the female length frequency. So now I have an age frequency that was generated by a male age length key with the male length frequency. So that gives me the true age frequency. I also have one that was generated from the male length key applied to the female length frequency. And I now have odd age frequency that is the assumption for that I would get from the male applied to the female one. I can play the same game by taking my age frequency that I got from the first set of data, and I can subsample that age frequency many times and generate pseudo sets of data to compare back to the original one to see how stable my age frequency is by a manipulation of the number of individuals at age, at size, based on the original sample. So we generated some software, and the typical approach was to take 50 bootstrap simulations, choosing from the original age frequency, a series of individuals with replacement that were in exact proportion to what generated the original age frequency. And that's, by the way, pretty important. And then calculating an age frequency for that pseudo population and comparing it statistically to the original age frequency that I got from the original sample. And if things are stable, or I should get the same age frequency back for each of those simulated populations, right? Okay. So we used 3 tests, and I'll bet that's not in here. So we used 3 tests. The first one is a runs test. What the runs test does, it says I have 2 frequency distributions. If they're the same and I do a cumulative frequency distribution, they should cross each other a random number of times. If they cross more than a random number of times, it means they're a really tight fit, right? If they cross fewer than a random number of times, it means that they don't look the same at all. For example, if I have 2 parallel lines, they never cross, okay? That's a highly significant non-random expectation out of the runs test. If you have 2 distributions that never cross, right? So I'm looking for cases where they cross a lot of times, or at least a random number of times, if I have the same distribution. The second test is the Kolmogorov-Smirnov test. Some of you have used that in here. This is a test that is used a lot to, for example, determine whether a distribution is normally distributed or not. I bet everybody in here has used it for that. There are some issues with the KS test. The biggest issue is it focuses on the center of the distribution. The way this test works is it's looking for the biggest deviation between those two distributions. And although you can get that biggest deviation at the start or near the end, generally speaking, the way you get a big deviation is to sum up a whole bunch of smaller deviations. And that occurs predominantly in the center part of the distribution. So if I have a humped curve, a parabola, for example, and I'm comparing two parabolas, the KS test is going to be very good at telling me whether or not the peaks in those two parabolas fall on top of each other. It's going to be lousy at telling me whether the tails fall on top of each other. So the KS test is a center distribution focused test. Okay? But it's a powerful test there. Anderson-Darling is the same kind of question that the KS test asks. Are the two distribution functions the same? The thing about Anderson-Darling is it focuses on the tails. It's profoundly sensitive to deviations in the tails. Now, if you open up your SAS routine or your R routine, you're always going to see that you can use the Anderson-Darling test to check for normality. If you look at the literature, I defy you to find a single case where somebody has said they've used an Anderson-Darling test to test normality. And the reason for this is that it's so sensitive to the tails that it's almost impossible to find a case when the two are not significantly different. And of course, nobody wants to report that. So they don't use it. They use the KS test, which always says they're the same. That's right. So you ignore the tails. Okay. So the Anderson-Darling test is very sensitive to the tails. I can tell you one thing that's interesting about this. I think it's changed. When we first started doing this, you could not find online anywhere a two-sample Anderson-Darling test. So we programmed it. And you could not find online anywhere the test statistic metrics, which it turns out were published in the Malaysian Journal of Mathematics. Yes, honest to God. So, so I'm pretty sure we're the first people that ever really seriously used a two-sample test. I think there's an R capability now. I think Kathleen said that. I won't swear to it. But anyway, we're going to use those three tests. What you need to remember is the runs test is really different from the other two. The runs test either shows that they cross a lot or they don't cross very much. Doesn't care about the deviation. One could be a big sine wave and the other could be a straight line. And that would be a non-significant runs test because it crosses a lot. Okay. The KS test is center distribution focused. The AD test is tails focused. Okay. And you can compare Kathleen, and she's got a paper just out, and it's in Journal of Marine Biological Association, United Kingdom. It got its volume number last Friday, I think. So it is available. And she has used a binomial test to evaluate the probabilities of getting a certain number of significant results. I'm sure most of you will know what the binomial test is. I'm not going to go through it, but it's a standard test to evaluate whether or not you got an unusual number of significant results. And that paper is about Georges Bank, and she's writing one right now on the Long Island data set. We should have, I'm hoping, Fish and Wildlife permitting, that y'all will see a draft of that in the next month, because it was pretty much done when she defended her dissertation. She just needs to pull it out. Okay. So how the age length keys. So here we have Georges Bank. We aged a bunch of males. We generated an age frequency, an age length key with the male data. We applied it to the male length frequency out in the field. We got a male age frequency. And then we asked the question, how reliable is that? And so then we subsampled that male age frequency many times, generated independent age length keys, applied them to the original male length frequency. If at least internally to the data set, this data set was robust, we should not see many significant differences, because every time we generated a pseudo age frequency, it should be very similar to the original age frequency. Okay, and in fact, KS tests very rarely diverged more than 2%. In other words, if I did 50 simulations, 2% or fewer were significantly different. Okay, so the age frequency that was generated is highly robust to subsampling based on the KS test. The age length keys were not interchangeable between groups. So if I subsampled the male one and then applied it to the female age frequency, they were significantly different 98 to 100% of the time by KS. So the age length keys were different for females and males, highly significantly different for females and males. Okay. You can't use the female age length key for males. You can't use the male age length key for females. Georges Bank, as you'll see later, is the most well-behaved age frequency. So if it doesn't work in Georges Bank, with absolute certainty, it's not going to work. Long Island, again, internally, male to male or female to female, no significant KS tests. Okay, I mean, it's a very solid age frequency from that sort of a test. But if you mix and match, 84 to 100% of the time it fails. And this is the center part of the distribution that's failing, right? Not the tails. So it's the part of the distribution you should be most easily able to fit, because you have more data there than anywhere else, and it's going to fail. So you can't. So the male age length key and the female age length key are different. Okay, what about comparing Georges Bank and Long Island, for example? Well, if the age frequencies are the same in Georges Bank and Long Island, if I use the female age length key from Georges Bank and apply it to the Long Island length frequency, I ought to get an age frequency that's the same as if I used the female age length key from Long Island and applied it to Long Island, right? I ought to get the same thing. KS says no, 100% of the time they're different. So the female age length key on Long Island and the female age length key on George's Bank are not the same. Ditto for males. So you're going to see later, and I'll kind of give you a hint right now about what the issue is. The problem with age length keys is the lengths, right? Females grow faster than males, which means that the age distribution in a 5 millimeter interval for the males is different from the age distribution in the same 5 millimeter interval for the females. And as a consequence of that, you can't mix the males and females. Okay. So it's strictly the underlying problem that exists is the simple fact that females grow faster than males. And you're going to see that later. We've got a lot of data on it, so it's going to coming at you after lunch probably. But that's the profound problem with respect to age frequencies. Now, the interesting thing about this, though, is if I lump the males and females together, okay, and I just asked the question, do I have a problem with the same kind of analysis population-wise? Okay, the population age length key is reliable, right? So female to female is reliable, male to male is reliable if I mix them together and I have enough animals aged. The population age frequency is reliable. So I get away a little bit from this male-female problem by just saying I don't care, because I can just age the population and I'm going to get my age frequency. I do pay a penalty, and I'll show you this a little bit later on. I do pay a penalty because it introduces more variability in each of the size classes. And as a consequence, it's likely that you have to age more animals per size class. But on the other hand, I don't have to sex them on the boat. So, you know, there's and I've only got one age frequency I have to worry about. That's later on, but in George's Bank, it was roughly 1.1 to 1. So it's close to 50%, although statistically it's different. Out in virtual land, Daphne asked what was the sex ratio in those samples. Long Island, it's a little bit different. I think it's 1.4 to 1, something like that. Males, yeah. So, and we have a lot, you're going to see a lot more about that later on, but there's definitely, the two populations are definitely different with respect to the male-female ratio, although they're not highly aberrant, right? So Kathleen's statement here, at least for her two sites, we'll see what Jill says, is that the sex-specific data may not be required to generate a population age frequency. But you might need the sex-specific data if you're going to do anything with the lengths. It depends on what you're using the lengths for. If you're using the lengths as a surrogate for age, then you're dead on arrival because the lengths are different. Okay, so that's the problem there. Oh, here's the George's Bank paper. that just came out in the Journal of Marine Biological Association of the United Kingdom. You shouldn't have any problem. It's on their website. Just go to the website and get the hemium in all paper. And it's, I don't know. I mean, anyone that's at a university can get this. I don't know if it's freely available.
It is freely available, I think, because I will need to.
Oh, okay. We might have paid for that. I'm not, I can't remember what we did. So anyway, it's, you know, it gives you a lot of details about this particular issue and all the gory statistics. So Jill's going to talk about New Jersey. I don't know if you showed a map where your sites came from.
I will.
Okay.
All right, so I just want to preface this by saying Eric and I ran these analyses this past Friday.
Yeah.
So we need a little bit more time to go over them in detail, but these are just the very basal results of what we have. Grain of salt, yes. So just to tell you, in general, I do have two sites. NJ1 is located directly north of the Hudson Canyon. It's a little bit west of Long Island. NJ2 is directly south of the Hudson Canyon. So that's the big difference between these two sites. And I do have a map in a later PowerPoint that I'll bring up and show you guys to see where everything is directly. So 777 were collected from NJ1. We used about 738 for aging. 900 plus were collected from NJ2, and we used about 790 for aging. And like Eric talked about, we use the KSAD and the REMS test to analyze these as well. So very basic results at NJ1, males and females were both incredibly statistically different for both the KS and the AD tests. I believe it was 100% of the time they were statistically different in both tests. Same thing for NJ2. So you can't lump these sexes together at this region at all, or my recommendation is that you shouldn't. And then we went through and compared NJ1 to NJ2 at the population level, and they as well were statistically different, which we'll see a little bit later on. Their growth is different, their age frequencies are different. So these populations, because of that Hudson Canyon barrier, are very, very different, even though they're pretty close. Now, interestingly, females, we also analyzed males to males and females to females. Females were somewhat significant. There was one case where we ran this, Eric has it built so that we look at the raw data file, and then we look at a compressed version of the data file that's focused on the median. So when we're focused on the median, females were not statistically different. But they were just looking at the raw data file, and we have kind of like the same trend for males. So potentially, kind of as we look more and more at these, we might not have to have like an NJ1 and an NJ2 males, females. We could just do males, females for NJ1 and NJ2.
So I'm going to credit Dan Hen with this idea. The problem with these statistics, both Anderson Darling, NKS, and runs, actually all of them, is the long tail in the age frequency distribution, which you're going to find out about pretty soon. And that long tail, which doesn't have very many individuals in it, which has a number of zeros in it for certain years, can control the statistical analysis. So the issue is what to do about that so that you minimize that problem if you want to. The analogy is chi-square. Some of y'all have used chi-square tests. There's a rule in chi-square. If I have a cell that has fewer than 5 individuals in it, I'm going to lump it into the adjacent square, okay? It's a routine strategy because chi-square if the numbers per cell are too low, causes problems with the chi-squared statistic. So this compression of size classes or any kind of classes that have few individuals in it is something that's not new. I mean, every single statistics book that has chi-square in it will talk to you about this. So the idea was that we would compress the tails the same in a chi-square-like process. Now, in chi-square, you have a rule. I mean, it's the number 5. The problem is, what rule are you going to use to say there are too few animals in this particular cell? And we investigated 3 rules. We investigated taking the mean across all the cells and compressing any cell that was below the mean such that the final number was above that original mean. We did the same thing for the median, and we did the same thing for the 20th percentile of the district of the numbers. And I won't go through everything, but we ran a whole lot of different evaluations, and the median seemed to behave the best across everything. I don't have a statistically valid way of saying, you know, it did significantly better, but I can tell you that just looking at the outcome, it was routinely the stabler thing to use. And so we decided, we have run all the statistics. So if someone wants to know, you know, what if you use the mean instead of the median, I can tell you, right? I can tell you, but what we've used to compress the low numbers is the original median in the data. Now, the result of that is that you take away a lot of the signal that is being used by the Anderson-Darling test to generate a significant difference, okay? And you eliminate a lot of noise, basically, as far as the KS test is concerned. So it typically generates different statistics. So when Jill says that you know she used the compressed test, this is the one based on the median in which we've lumped low cell numbers. And it can be compared to the case where we kept everything in. I should say one other thing. I have routinely all the way through eliminated double zeros. And the reason why is because double zeros increase the N value of the test, but in my opinion, tell you nothing. And so I have always, all the tests are done eliminating double zeros.
So just to wrap this up, in my recommendations, just on, again, the very basal level of this data, males and females are statistically very significantly different from each other in their respective populations. So that would be a recommendation of, yes, choosing a sex-based key, but it might not be necessary per population. So females in New Jersey might be growing around the same rate between these two populations, but they're very statistically different from the males. Both NJ1 and NJ2 are very, very different from each other. So separate keys for those two populations are highly recommended. And one more step that we are going to do is we are going to run these same analyses between NJ1 and Long Island. As we'll see later, the growth rates and the age frequencies between those two sites are very, very similar. So we might only need one key for that region. Any questions? Nope.
I got a question.
Yes.
If you look at it across the entire range, how many different keys would we need? 4?
So for Zoom, Guy's question was, when we look at their entire range, how many keys would we need? And that's going to be kind of our biggest discussion, I believe, coming out of this workshop, is if we have 2 keys for males and females per population, and that would drastically increase our numbers. But if we're finding that females are growing at a same rate across a certain area, then we only might need like 2 or 3.
So that's a really good question, a really good one. And the big question that comes right back at you about it is, if I'm going to get a stock-wide age frequency for a model, how am I going to get it? Where are we on our agenda?
We're at number 4 on the age frequencies.
Age frequencies next.
Mhm.
Okay, you've heard all the preliminaries. It's good now. Okay. Age frequencies. If you come up and beg. Okay. Age frequencies. This is what George's Bank looks like. George's Bank was one, by the way, that that Sarah Pace did also. And I should generate a little preliminary about this. So when we did Sarah's work, we didn't know about the sex differences or how many animals to use, a whole bunch of things we didn't know. And we aged about 100 or 150 animals for each of the age frequencies. Now, that's clearly not nearly enough. But what Sarah did was make an interesting assumption. And her assumption was that if I have a 0 for an age, in other words, a missing cohort, it's highly likely that that's due to undersampling and not the fact that there were no animals in the population that were born that year. And she applied that assumption to her data set, which is essentially a smoother that smooths out an erratic age frequency that results from having undersampling. And if you compare her age frequencies with Kathleen's, they're really similar. So that assumption is actually an interesting assumption to contemplate. If I have to undersample, can I smooth out the age frequency, and is that a reliable thing to do? And the comparison to Sarah's work would suggest pretty strongly that it might be reliable. I mean, I don't know how you'd sell it to the SSC, but you know, in my mind, if I could only afford to age 100 animals, that's exactly what I would do. It's what Sarah did. Okay, so here's the George's Bank age frequency with a couple of notable times on it. And the big deal here, obviously, is that from about 1880 until about 1960, there are a lot of animals. Now, there are not very many animals after 1960 because of the dredge selectivity, okay? And there are not many animals earlier for a reason that we need to discuss before we leave this meeting. Because either it's because of mortality, or it's because of recruitment, or it's because of mortality and recruitment. Okay, so that's a decision, but something happened, obviously, around 1880, there's a lot of animals. Her oldest animal is way out here, a little bit, some years before the Declaration of Independence on George's Bank. And really, if you went out there and sampled the population, the likelihood that you would have an animal that was born before the Civil War isn't too bad if you knew how to identify it.
Eric, quick question on that. Just out of curiosity, with all the, and this was 2015, correct?
The lengths came from 2015. The aged animals came from 2017.
Okay, so we talked a lot about error and accuracy. Has anybody just gone back and taken that particular cell and had a couple of people age it to see if it was truly before 1776?
I don't know if that was one of the ones that went through the that process or not.
That's an outlier.
Well, yeah, there's a big, but you know, there are, here's 1800,
Yeah.
right? So while George Washington was president,
Yeah.
you know,
Good bar though.
exactly. An interesting thing that comes out of here, the recruitment peaks are on approximately 8-year intervals. Now, Kathleen ran an analysis called wavelets. I'm not going to show it here. If people are interested in wavelets, you're going to see it in one of the papers she's going to publish. But it looks at whether or not there's cyclicity in data sets like this. And she came up with a significant spectra with cyclicities in 30 and 60-year timelines, which is the Atlantic multi-decadal oscillation probably. And the 8-year number is possibly a harmonic of the AMO. However, the other thing that's interesting about 8 years is that the North Atlantic oscillation has a cycle of around 8 to 10 years. Okay, and the NAO is an important piece of what controls water temperatures. Now, you know, the AMO and the NAO conspire a little bit there, but the NAO is an important feature. And this 8-year cyclicity is very clear, and it extends over most of the record where there are enough animals around to really show it. Okay, so on George's Bank, you know, basically every 8 years there's a big recruitment event, but in between, generally speaking, there's recruitment every year. Here's Long Island. Long Island's got a relatively similar shape to George's Bank. The number of animals increases around 1890 or so. Because of dredge selectivity, ceases in the or drops down around 1970. If you read the Harding et al. Paper, you're going to find out that we said some words in that paper about recruitment event in the 1980s, and that looks like that. But you can't assume that it was a small one because these animals are still too small to be caught by the dredge effectively. The other interesting thing, here's the Declaration of Independence. So now, Guy, there's a lot of animals older than that. Okay. Carl Linnaeus was born in 1707. That's the oldest clan we found, born in 1707. Do you know what's interesting about that coincidence? Daphne? Carl Linnaeus is the person who described Arctica, Icelandic. So, yeah. So, but, you know, named it. He's the person who named the animal. Yeah. He named everything. But this clan was born on the year he was born, and he named the clan. Not this particular one, all of them.
It's too bad we didn't have some young ones, we could have flew down there.
Yeah. But anyway, the difference between this one and the other one, just to go back here, is the extensiveness of that long tail, right? So that Georges Bank, the number of animals, you know, drops out dramatically about 1870, going back further. And if you look at where 1870 is on this one, there's a hell of a lot of animals out from that. Okay.
Hate to interrupt you, Eric.
Okay. So folks, in virtual land, it is roughly 12:15. And I would suggest that we convene again at 12:45. Is that okay? So we will convene again at 12:45. Okay, so we're picking up pizza. I'm not proud. What? There's some here, but there may be some in that.
There are, I got plates. There are plates. Yep.
So the question is that increased animals in the late 1800s, an artifact, the fact that they're dying at 2 or 3% per year. So you would expect that decline exists. Or is it because all of a sudden it became a really good time for those to die?
I don't know. It's not really way to keep that part of it.
They're entirely conflated.
So this maybe remember.
I'm gonna let you talk about age frequencies before I start doing that. Yeah.
Joe, have you started?
Yeah,
I don't have paper.
no, it's my internship paper. Yeah, so I just got comments back on the board, and I think after that round of comments, we're gonna send it out. I don't know, should be ready soon.
Now, she's gonna be doing a lot of writing this summer.
We're good.
Okay, is everyone,
Yeah, that's right. Yeah. Yeah. Sure enough.
Eric, I think we're off our.
hey, Eric,
Land and sea.
Eric.
Call room to attention there.
Too loud, people are taking it in.
Okay, we're called back to order.
okay, so Eric wasn't quite finished with Kathleen Hemion's age frequency, but the latter half of her PowerPoint goes into mortality and longevity, which is item number 5 on our list of terms. So in keeping with item number 4, I'm going to go ahead and give my results on my age frequency. So very similar to what Kathleen did, we have the relative frequency on the y-axis and the birth year on the x-axis. You can see that a large bulk of my population was born in the 1900s, specifically around the 1930s to the 1950s, right in here. My youngest animal is about 13 years old, and my oldest animal is all the way from 1733. So as Guy was talking about earlier, with the long-tailed skew and that one kind of random outlier in Kathleen's Georges Bank data set, we do have a little bit more very old animals here as well. So compared to NJ2, NJ2 is a little bit more standard across the board across the past 200 years. There was a pretty big uptick in recruitment in the 1990s, which we can see here at the very far right end. We reached about 50% of the population in 1920. And then about 75% of the population was born in and around 1982. And for this one, our oldest animal, again, is all the way back in 1741. So again, we do kind of have that similar tail getting very small down into the 1700s.
I'm just going to make a couple of comments. Go back to NJ1 for a minute. Well, you're going to talk about this being similar along,
Yes.
right? Yeah. Okay, I won't say that. Then go to NJ2. The interesting thing about NJ2, which you can see right away in comparison to all the other ones, is that the peak in population abundance is earlier, and there's a apparent decline going into the 1960s. And then, of course, there's this recruitment event over here, which I think is the recruitment event that Julie Harding and Roger and I saw when we went out and sampled and published that paper on that. But the thing about this high right around the Civil War is that that's really distinctive from the places further north, and it's pretty similar to Sarah's New Jersey station, which is south of NJ2. So it's possible that the population dynamics south of Hudson Canyon has been quite different over a good bit of that region relative to what's off of Long Island and extending to Georges Bank. The age frequencies are relatively similar between Sarah's and this one, and very dissimilar to the ones further north. Go back to the one before. The one interesting thing about this one, and I'll just throw it out real quick, is that the 30s, 40s, and 50s into the early 50s are the last big warm event prior to now. So it was cold in the 20s. It was warm in the 40s. It was cold in the 60s. That's probably an NAO-like thing. But, and then of course, it started warming up in the 80s. So you see, this is at least coincident with the World War II warming event. And Julie and I argued that there was a pretty big recruitment event in the early 1950s off of New Jersey and Long Island, which would be these animals here now that Jill's got. My 2 cents.
Yes, so looking directly between NJ1 and Long Island is on the right, NJ1 is on the left. We can see how very kind of almost eerily similar they are. Now, when we ran these through our KS and AD tests, pretty much they were very, very similar on the KS level, which is again at the center of the distribution, and with the run tests. However, the only difference occurred in the AD tests for the tails, which we can see we do have this random uptick here on the right that is not really seen in Long Island, and we believe that's where that difference in the Anderson-Darling test came from. Other than that, they're pretty shockingly similar. Yeah. So,
There are no standard Quahog dredges.
So,
No.
so Daphne asked us if we had used the same dredge for both boats, and they were both commercial Quahog boats or
Yeah,
Quahog
one
dredges.
sample, the Long Island sample came from Pursuit. And the New Jersey sample came from the
Big Bob.
I just wonder if you are picking up that signal in the 2000s and not with the Pursuit.
It could be, but I don't know.
Yeah, Daphne also asked if maybe it was just a difference in dredge selectivity that we picked up more animals in the 2000s. My other guess is that because there's a 2-year offset between when these clams were collected and mine, maybe in those 2 years, more could have possibly reached a size that was picked up by a dredge or able to be picked up by a dredge.
Actually, it's applied to the length frequency also, and the length frequency is 2015 versus 2019,
19,
right?
yes.
Yeah, so the length's 4 years old.
Yes. So just in case anyone on Zoom didn't hear, Eric said that the length frequency that we used was actually from 2015, not 2017. So there's also a 4-year difference between these two data sets, in which case more animals could have reached a dredgeable size. So just on some next steps, I still need to process the mortality and longevity rates, as Eric is about to talk about next. And I'm also going to go through and identify recruitment trends as they relate to the AMO and the NAO, like Kathleen was able to map in her age frequency curves. Any other questions? Okay, back to Eric.
Kathleen was nice enough to work out and label it magic and R. We have it in MATLAB, but there is an R package now, and she was able to run it around the block. So that's basically ready to go. Is this the next one on our agenda? So any other questions about age frequencies before we go on? Hearing none. So what Kathleen did was fit the standard mortality plot to the backside of the age frequency for George's Bank. I mean, there's no magic here. It's the standard regression approach. And the male mortality rate comes out to be 0.04, the female 0.05. Those are somewhat higher than we use in the assessment, which I think is 0.02, right? Dan? Something like that. I think I'm betting it's 0.02. Yeah. Now, of course, the assumption here is that none of the shape is due to differential recruitment when you do the mortality plot, and it's a long time. So, you know, that the assumption that recruitment hasn't varied over 200 years is really, stretching it a little bit, probably.
It shouldn't matter the difference between the instantaneous rate and
Yeah. It's based on the annual cohort. Actually, I think she put these into 10-year boxes to reduce some of the noise. I have to go back and look at her paper, but I think she's plotting 10-year boxes. Uh-oh.
You've got males at 244, females at 217, then you have a population at 257. So
Yeah,
that's just the oldest. That's the
there's an equation to estimate longevity. I think it might be a Honig equation. I just don't, I'm not going to die to defend it. Kathleen probably would. She's a big believer in it. I don't know. I think the mortality rate is an upper bound on the mortality rate because some of that could be recruitment. But, I do want to discuss later on whether it's feasible with all the data that we have to extract a recruitment signal differentiated from the mortality signal. That's a topic of conversation, and I have that later on, I think, down in the agenda. Long Island is 0.02 for both females and males, which is dead on what the assessment number is, for whatever that's worth. Right, dead on. And of course, the difference between the two is the Long Island one has a much longer tail. If you believe that that's all due to mortality, it's going to have a lower mortality rate. This particular calculation is not going to work very well for NJ2 because it's dropping on both sides of the peak. So some of this has got to be due to recruitment.
And then the question on Georgia's more driven by
I mean, so Dan's commenting about Georgia's Bank and recruitment, and I honestly don't know how to separate these two. I thought several times about trying to write a model of some sort that would try and fit various recruitment and mortality strategies to see what would come closest to the actual result. And I'd love to talk about that because I think that would be an interesting thing to try and do. Okay, summary on recruitment. Again, pulses occur in 8-year intervals, at least for Kathleen's sites. Don't know if that's going to be true for New Jersey sites. Maybe NAO. Could be that spawning is more successful with warm NAO anomalies. And I do think it's worthwhile going back in time and seeing whether some of the peaks are due to known warm times, because we do have some information about warm and cold shifts. So there was a warm event around 1900, for example, and we can take that back a little bit in time anyway.
Eric, when you refer to these historical warming events in 1900 and stuff, where do you pull that type of data from? Is there some kind of big chart somewhere?
So you can download time series for the NAO that are developed out of a variety of climate proxies, going back maybe 200 or 300 years anyway. Of course, they become more and more problematic, but people do have that kind of information. What the bottom water temperatures are is a complete unknown. Of course, that's what you would really be interested in. You'd like to know whether the cold pool is expanding or contracting and so on. So we don't have any information about that. There's a model run that I think Alyssa will probably talk about that's come out of Saba's lab in Princeton that I think gets back to, what is it, 52 or 58? 58. So there's a retrospective that has bottom water temperatures in it that goes back to 1958. You know, the first actual measurements aren't anywhere near that far back. Once you get past that, there aren't any bottom water temperatures. There's a couple of long-term proxies that you associate with temperature. One of the big ones is the coral and algal proxy from Labrador Sea, which I think goes back around 1300 years. But I'm not sure to what extent they've actually pinned the temperatures on that. You can see the AMO signal in it. So there's clearly temperature information in that. And you can see the little ice age in that time series. And that's all from one coral and algae that was collected.
Just curious.
I don't know if there's anything on here. Natural mortality Georges Bank is higher than the rate used in the current assessment model. Oh, yes, I need to say something about the parenthetical. Estimated instantaneous mortality at Long Island is lower than the rate used in the current assessment. Kathleen's dissertation defense, the committee made a recommendation to look at develop some statistics around the mortality estimates. And she is in the process of doing that, but we don't have them yet. It would be feasible to do that based on the software that we were using to compare age frequencies and age length keys, because each one of those random draws, in essence, generates a data set from which a mortality estimate could be created. And so there would be a possibility of developing a standard deviation around the mortality estimate from that. And those simulations have all been run, but I know she hasn't gone through yet and gathered up all the information to do the statistics. Yeah. First point, pretty interesting. So if the question is, when did the little ice age end? And there's quite a bit of discussion about that, as Alyssa found out when she put a number in her paper that's coming out in the Holocene Journal. And one of the reviewers was moderately upset about that. So you can get anywhere from 1800 to 1850 as sort of a time for the end of the little ice age. If that uptick in numbers is a recruitment signal, at least partly, then recruitment increased at the end of the little ice age in the late 1800s in the northern region. And earlier than that, off of New Jersey, as you saw from Jill's data, and which would be consistent with an expectation based on no evidence that it warmed up faster down south. The timing is, this is another one. There is one other age frequency in particular that's published, and this is one out of a lock in Ireland. And the shape of the age frequency distribution is very similar. It's based on a much lower number of aged animals. So it's It's more spotty. But the overall shape of the frequency distribution is pretty similar. Atlantic multi-decadal oscillation, low temperature anomalies coincide with low recruitment years. That's for sure on Georges Bank. I think it's true for Long Island. So the AMO signal is definitely in the wavelet analysis. Okay, so the recruitment AMO cycle is about 60 years, 50 to 70 years. And that cycle is clearly present in ocean cohogs. Now, whether it's a mortality signal or a recruitment signal, but the AMO is definitely influencing the population dynamics over that scale of years. I'm going to comment about stability later on. I'm going to remember before we end up getting you to think of, in fact, I'll say it now in preparation for what you're going to see later. I wonder, when we do population assessments, when we talk about biological processes, in large measure, when we do any kind of modeling of them, we assume that the populations are in equilibrium with the environment. And I don't think ocean cohogs are ever in equilibrium with the environment. I think they're perpetually out of equilibrium, which means that the entire population process in ocean cohogs is different from any other common species that's been studied. I think that's the biggest impediment to dealing with these animals is the fact that they are never in equilibrium with the environment. So when we get to the end of all the information and everything, you can tell me whether you believe that that's the right way to look at ocean cohogs.
So what would make them, what would there have to be demonstrated to show you that they are in equilibrium?
It'd be tough because they live longer than the climate cycles. And climate cycles are when we talk about equilibrium, we're talking about within a climate cycle. Okay, and climate cycles generally are responsible for maximum ages.
Well, learn to burrow deep into the mud.
That's right.
When there are unfavorable climatological.
That's right. So they're out of equilibrium.
Wouldn't that make them in equilibrium with the
No,
environment?
makes them out of equilibrium. Yeah, makes them out of equilibrium with it. Yeah. So I guarantee you, by the time we get done with growth rates and stuff, I can make you a believer about that comment. Jill, do you have anything more on this? No. Alyssa, can you come up with the agenda so we can see what we're doing?
Hey, Eric, when did the little ice age start?
Guy asked, when did the little ice age start? Okay. Alyssa is the expert on that, but
Alyssa?
Start and end is debated, but somewhere in 1200, around that time.
late 1200, early 1300.
Roger just wanted to add that.
Yeah, whether or not I don't believe you probably.
Yeah, so there's Roger's comment. Yeah, I mean, the little ice age, the coldest part of the little ice age, I think there's some agreement about this. The coldest piece in the little ice age was the second half of the 1700s.
Okay.
So if you ask the question, how cold was it at Valley Forge in the Revolutionary War, that's as cold as it was in that region of the world since 3,000 years ago. But George Washington really picked a lousy time. Okay, so sex specificity. What do we have to talk about on that? Yes, I think there's a Kathleen thing, right? Dimorphism. Okay, you're gonna like this one. Okay. Just remind you that again, we used those tests to compare male and female distributions, the lengths and the ages. All the stats are based on those methodologies. George's Bank. Okay. The upper plots, one in the middle, the cumulative distribution plot, is lengths. Dashed lines are the males, solid lines are the females. Females are all set to a significantly larger median and mean size. Okay, and you can see that on the left under item A. The x-axis is length for A. The box on the female plot are the 25th to 75th percentiles. The line across the middle is the median. The plus is the mean, I think, assuming it is. And the females are distinctly larger than the males in George's Bank. And you can see why the runs tests are always significantly different between these two, because they're basically in parallel. They don't cross each other at all. This is a very distinctive difference in length frequency. The age frequencies, and this is C and D underneath, are almost identical. So it's not that the males are dying younger than the females or some funky business like with summer flounder. These animals live effectively the same length. It is true, and let me see if she says, it is true that the oldest animals tend to be males. So there's a little bit of something in there where when you get out to the last, 1% of the cohort, it's likely going to be a male. But over the age range as a whole, in George's Bank, the age frequency is essentially identical for the males and females. It's the lengths that are different. So female and male length frequency distributions are significantly different for the KS runs and AV tests. Oh, sorry, the females are the dashed lines. They're offset to larger sizes. Yeah. There's no significant difference between the population female and male age compositions. That's C. And in fact, statistically with the other tests, you don't see a difference. The population is sexually dimorphic, but it doesn't influence the age data. So if you want to get away from the male-female problem, you want to use ages because it effectively eliminates the male-female difference. Here's Long Island. This is a big ditto. Exactly the same thing to say. You've got the length difference on the on A and B up there. The females are bigger for a given length. You have identical age frequencies, essentially identical age frequencies on the lower two plots. So there's simply, this is probably a species-wide phenomenon. It's not local to a population, okay? Females are always bigger than males at age, at a length. They're going to have the same age frequencies. You can look at the sex ratios. On the left is George's Bank. Sex ratio is 1 to 1.1. The 0 line marks an even sex ratio, same number of males as females. The colored bars to the right are cases above the 0 line, which means there's more females than males. The open bars, which are mostly on the left, are cases where there's more males than females. And you can see that the switchover is between 90 and 100 millimeters. So right in that, in that size class for George's Bank, it's just about as many males as females. If you go and sample at 80 millimeters, you will have a sample that's well biased male. If you sample at 110 millimeters, you will have a sample that's well biased female. Long Island is exactly the same, really. The crossover point is a little bit smaller. It's between about 85 and 95 millimeters. The sex ratio is 1 to 1.4, so there are more males than females there. But the differential is the same. What I was hoping for when we came up with George's Bank was that this change in sex ratio with size would be a general population-wide relationship. But it's not. It's obviously regional because George's Bank and Long Island are different. So I couldn't predict the sex ratios for George's Bank from the Long Island relationship and vice versa. Good question. So Dan has asked, are they protandric? So the first person who noticed the male-female differences, I think, was Ropes. He wrote quite a little bit about it, and he argued that they can't be protandric. It's got to be separate sexes that are doing something different. That sort of observation and agreement has continued through some other works between now and here, and we totally agree with that. There's no way to explain what's going on by protandry. And clearly, based on the age frequencies, it can't be explained by differential mortality rates. So this is the simple fact that the females grow faster than the males.
Why can't they be protandrics if you start out growing fast, if you choose to be a female and you continue to grow fast over time? I mean, I guess it doesn't really matter.
You could, for example, if you go to oysters, you could generate a plot that looks a little like this for oysters. But if you then generated the age frequency in oysters, you would find out that the male oysters were all young and the female oysters were mostly old. And in this particular case, the age frequencies are the same.
Yeah, I was just wondering if it was a function of a certain length, but certain age. Like if you hit the age of maturity and you're big, you go female.
Oh, I see. I don't think anybody's looked at chromosomes. Okay, clams generally are XY or what's the other one? WZ or something like that. It's the question is, is the animal with the same two chromosomes female or male? In some cases, like people, XXs are female. In other cases, having the two chromosomes the same would make the animal a male. And I think that's called WZ or something like that. I'd have to go look. It's not XY. It's got a different terminology. But I don't think anybody's looked at it. And Arctica is very weird. But generally speaking, in the clams, as you would consider them, the very high taxonomic group clams, they are separate sexes. Protandry is an interesting problem. I think there's a slide here. Let's hope. Yeah. So dimorphism is rare in bivalves. There are cases with large females and small males, and by small I mean they're typically parasitic males. Okay. Protandry, it's common, or hermaphrodism. It's common in the true oysters, in the pearl oysters like Pinctada and those related ones. It's common. The pinids, it's common in the pinids. All of those are obviously not clams. If you go to the venerids, for example, or the veneroids, Roger, I wish Roger were here. He could tell me what to call it higher taxon. I'll be willing to bet you won't find a single case that don't have where there's anything with separate sexes.
Okay, yeah. I'll stay on this side.
At any rate, so this is highly unusual. Who knows why they do this? Okay. My own pet theory is that the males mature first. And when they mature first, their growth rates slow down. And during that period of time, the females continue to grow because they're not mature yet. And that gives them, gets them to be larger than the males when they mature, okay? And if you go back, what's this? It's not up there. Yeah, so Roger's talking about oysters there. Now I've lost my thought.
Well, females are bigger.
Oh, let me go back and show you something. Hold on a second. Yeah. There's the little thing. Here we go. See, the thing about these plots, the thing about these plots is once they separate, they are parallel. So it's almost as if there's a point in time when the growth rates differ. And once both sexes are mature, the growth rates are proportionally the same. So the length, the cumulative length distributions don't continue to separate or anything. They just follow each other, right? So it's probably a maturity issue where one matures earlier than the other. That would be the expectation. I don't know of any data where it's been looked at, but that would be the expectation in my mind. That if we actually had that kind of data, we would see that. Now, if that was true, arguing about why males would mature sooner than females is pretty straightforward based on the general theory of energetics and sex. But so it would be an expectation. The odd thing is, given that all possibly being true, why is Arctica the only one that's done it? Because if this was an important energetics thing, certainly some other clams would have done it. So anyway, it would be an interesting thing to think about.
I will say this, I think in section 8, when we're gonna get to it, my internship with the ISF did a lot with examining the growth rates in males and females. So we can talk about it more then, I can show you some of the link data that we have.
So Arctica is sexually dimorphic, females generally larger than males. Georgia Bank and Long Island have significantly different length and age frequency distributions. Population sex ratios for large animals are skewed to male dominance. I didn't show you that, I guess, but there are she's got that worded wrong. It's less than 60 millimeters. Males generally dominate smaller size classes. Yeah, females generally dominate larger size classes. So that's the case. Do you have anything on this? Okay. Show off New Jersey.
So I'll just show you my graphs because they're pretty similar. We did do again some statistical test work on this, but this was within the past week, so we need to go through it again to be sure about what the numbers are telling us. But so this is NJ1, and interestingly, in NJ1 for ages, which is the top graph, females are actually a little bit older than males rather than the two lines being completely on top of each other at all time. And then with the cumulative length graphs on the bottom, we see that females are again much larger than males pretty much at all times. For our statistical tests, pretty much almost everything was significant except for the KS test for length. But again, I need to go through that and make sure that I was interpreting it correctly because the numbers were a lot and I got them very recently. So for NJ2, it's a pretty similar story, but not quite. For the age frequency, the lines are much closer together. So females and males are at the same age at the southern site. But the same thing for length goes for the NJ1. Females are much larger than males, and statistically significantly so, pretty much extremely. But yes, for the statistical tests, I need to go back and double check and make sure. And those will be reported when I finish my thesis, but yes. So.
The trends are generally the same.
Yes.
Over all four sides.
Yes.
Let's see, show difference in the cumulative frequency. There is significant. We'll go back and look at So I guess that would support our hypothesis of some difference in survival. There's some function of mortality. But it's not. I guess it acts more on a smaller
Yeah, I mean, it's hard to speculate more than just these generalities, because we don't actually know what the answer is about why the two sections are growing differently. And we don't have the really young animals to identify the precise timing of maturity, for example. So we're sort of speculating pretty broadly, but in all four cases, the lengths are different. And in 3 of the 4 cases, the ages are spot on. In this particular one, they're not. It suggests that the common condition is to have the ages about the same.
Yeah, I mean, the easiest answer would have been that there was some, the F was responsible for the fitness because that would act on, that's, a size selective process that would act on mature animals, but they were the larger animals and smaller ones.
Yeah, we thought about that too. You're right. I mean, so you can't end up fishing in the sport here.
So that's it for me. I wish I had more to talk to you about, but I just need to work with the numbers a little bit more. Yeah, 3 more months.
Lots of stuff going to come out.
And then do you want me to talk about my internship data now or at?
Actually, this would be a good time for you to do that while you're up here.
Okay. So we'll go ahead and talk about my internship data now. It has quite a bit to deal with differences between sex. So for my internship, we decided to actually kind of look at this question on maturity and differences in sex-based size, really kind of looking at that sexual dimorphism in Arctica. So as we just discussed, sexual dimorphism is pretty rare in bivalves. It's really only in the cases of protandry and dwarf males, but that's not really the case for Arctica. Females are much larger than males. And as Eric talked about, the current running hypothesis is that males mature earlier than females, leading to them obtaining an overall smaller size. And we wanted to potentially investigate the degree to which that might be true. So here's just the evidence for that. Again, we just went over this. Just our cumulative length frequency, females being much larger, runs tests indicating that these animals are extremely significantly different in size. So for my internship, what we decided to do was try to find any statistical patterns between males and females and when females begin to grow faster than males. This might potentially indicate when animals reach maturity at our sites. So what we did is we looked at pretty much all 4 data sets, the entirety of all 4 data sets, Kathleen's, George's Bank, and Long Island, and my NJ1 and NJ2. We organized them into birth decades to attempt to mitigate any environmental influence on growth. And then we averaged the growth rates every 5 years up to year 50, and we applied the Welsh's t-test, or the t-test of unequal variances, to determine the degree to which these averages are different. So this is George's Bank. This is a graph of the cumulative ages up to year 50 and the corresponding p-value that the t-test produced. So the p-value you're seeing the p-values graph here. So this is the difference between the males and females. I just want to make sure that I'm clarifying that correctly so everyone understands. And each different line represents a different decade. So for George's Bank, we see that 3 out of the 4 decades become significant by year 15. So by year 15, females are growing to be much larger than males, statistically significantly so. For whatever reason, in 1940, they don't reach that threshold until year 25, excuse me.
This is based on
Yes. Yes, just for the Zoom audience, just a clarification, this was based on growth increments. And we can actually look at the different lengths between males and females over time. So when they're quite young at age 0 to 5, they're very, very similar in growth. But again, once you reach that year 15, even at year 10, you can see how much larger females can become than males. And for George's Bank, we often see a differential of 10 millimeters in growth difference by year 50, where females can be 80 millimeters sometimes and males are only 70. We'll look at Long Island next. So Long Island, we only have 3 decades that consistently reach that p-value threshold of statistically significant. 2 really don't. But again, for the 2 that do, they again reach it at 15 years. 1 doesn't reach it until year 30. And we have some theories as to why this site looks the way it does relating to environmental factors. But to look at the growth, you can see why these values are not statistically significant, because they're very, very similar, except pretty much in 1950. That's the widest growth difference between the 2 that we see. Otherwise, they're very, very similar.
And these are animals that were born in these decades.
Yes,
right?
yes. So then we look at NJ1, and NJ1 is our most consistent site out of all 4 that I looked at. So by year 15, every single decade reached statistical significance. And at year 5, 2 sites are already statistically significantly different. So by year 5, females are already 3, 4, 5 millimeters larger than males. And they just continued to grow larger than males throughout the remainder of the 50-year cycle that we looked at. We can see that again here. So especially like for 1910, again, we reached that 10 millimeter differential between females and males. Females grow to be much larger than males at this site at certain decades. Then we have NJ2. And NJ2 is kind of our mess that we've been trying to figure out what to do with. So for here, we only have 3 sites that reached statistical significance, but it wasn't until year 35 or year 40 compared to year 15 with the other sites. And we have 2 sites that don't reach significance at all. And at the very end, again, I have some theories as to why. But we look at this and we can see clearly again that males and females at this site are growing at the very same rate. We're only 2 or 3 sites, you can clearly see females growing at larger rates. So to try to figure out why we see these differentials, we looked at environmental data and we really focused on the cold pool. But first I want to show you that George's Bank is a northernmost site, and it's also our deepest site at 72 meters. LI is the most inshore site. So Long Island is this triangle right here. NJ1 is this one right here. So these 2 sites are the closest, which might explain why we see those similarities in the age frequencies. And then NJ2 is the one that's the southernmost site here. So I've been looking at cold pool data to try to figure out why we're seeing these differences rather than it being a species-wise thing, because it's not based on the data that we've seen. That because the cold pool fluctuates over this distance, we're seeing these huge growth differentials, or just differentials in general, excuse me, across sites. So George's Bank actually has pretty strong tidal mixing, which allows for a stronger heat flux, which might cause the differentials we saw at the earlier growth, but it's also the most northern site. So we suspect that it has the coolest temperatures to deal with, which is why females do grow to a much larger size than males. Long Island is the shallowest spot. So it's subject to much warmer or much faster warming rates. And we think that's why that males can keep up with females in growth. We think that the warmer it is, the more able males can keep up with females in growth. And NJ1 is located at the 60-meter isobath in New York Bight, and the New York Bight is the home of the coldest waters of the cold pool during its annual cycle. This site is also located at the center of the cold pool, where minimum temperatures are often occurred. And we think that's why females grow much larger than males here, is that males just can't quite keep up. NJ2 is the southernmost site, so it's constantly experiencing warmest temperatures. We think that's why males can keep up with females on a much more consistent basis. So just some hypotheses, we think why this might be happening. So again, we think warmer temperatures might allow males to grow at the same rate as females for at least a given period of time. This was clearly indicated in LI and NJ2. Oh, and I'm sorry, I forgot to finish this point. But cooler temperatures can create a pretty large differential between males and females. So why might males mature earlier? It's something that we're also looking at. Something that I found interesting was that there was evidence for hard clam walking and other clam species. So horizontal movement rather than just the traditional vertical up and down burrowing. And we think if males grow to an overall larger size, they use less energy to get to where the females are. This hasn't been seen in quahogs, but it has been seen in Mercenaria and Spicula. The other theory that I was really intrigued by is sperm limitation. If males don't produce as much sperm, then they might grow to a smaller size at maturity so that they can start to produce sperm earlier compared to when females would produce eggs, if that makes sense. I know this was a lot to go over, so if anyone has any questions, please ask me. I can try to clarify as best as I can.
So you were saying that your southernmost site is
Mhm.
near the southern edge.
That's my, I know it's the southern, I know it's technically still in the New York Bight, but it's the closest one that we have to the southern MAB.
I would think that's the pretty scary.
You would? Okay.
I don't know, do you have temperature sensors for that area?
We do, but they don't date back as far as my data does. So
No,
it's
sure,
hard.
but it would tell you now,
Yeah.
over the last
We,
year,
yeah.
whether those two You're kind of making that, you're suggesting that they're pretty different in
Mhm.
temperature. I don't know.
Mhm.
I
They're,
haven't been to them myself, but
yeah.
We
Yeah.
have the document.
Yeah, the sum of the time series data that I have looked at from the past 10 years does indicate that on J2 is warmer. So for me, it's interesting. Just some other patterns that we found is that by year 15, pretty much every clam was at least 50 millimeters, which bodes for our theory that clams mature at half of their maximum size. And there's some literature that has been produced, especially out of Iceland, where they found that all clams were mature by size 55 millimeters. So we think that our clams at least are maturing by year 15 and size 50. But again, when we look at NJ2, because it is at least a tiny bit warmer, we think that maybe they can grow to an overall larger maximum size because we're not seeing that growth differential well until year 35.
Anything else from the audience or virtual audience? No?
Because coming in with that long list of terms of reference, I was like, we'll just like touch on the top three. There's no way we're getting the like that whole list. And you have pretty much something for everyone. I just want to
been so many years, and I've been here before this too, but even we're now for a really long time.
So now,
So we're on.
Yeah, I really didn't think
Okay,
it
let's,
was
let me go down
It's
here.
like, we're not gonna be talking.
We've gone to some places where we're going to ask questions, but there's two subjects that we haven't covered. And I'm thinking about jumping down and talking about the growth data to get everything out on the table. And then Alyssa's data.
My growth data or my?
All of your data.
Everything? Like all my chapters?
So why don't we talk about your data except for the growth data?
You want me to
Next.
go through the whole scene and tap on them?
Yeah.
Okay. Right now?
And then that will get us into talking about the growth data where we've got some interesting things too. So for those who don't know the history here, quite a number of years ago now, there was a little bit of a tiff about closing off part of George's Bank. And a consequence of that is that Kelsey and I dug out all of the old Delaware 2 data from archives up in Science Center, scanned them all in, and put together a story about what was going on in George's Bank. And then we extended it throughout the range of the stock because we had the data. And one of the things that fell out of that was the case that there was a bunch of sites where ocean quahog shells had been collected, but never any living animals, which of course should never be. So we speculated in that paper that those were sites that had been occupied by ocean quahogs in the past when it was colder, but no longer because the world has warmed up. So by happenstance, probably in 2019, I'm not sure, when did we collect your shells?
2019.
Yeah. We had a cruise
Prior to
on
me.
the Betty Sea, and we had a few extra days at sea, and we sampled a bunch of the Delaware 2 sites between roughly Delaware Bay and Chesapeake Bay, and collected all of the ocean quahog shells that came up at those sites, figuring that we'd send a few of them out for C14. So we sent 25 of them out for C14. And what we got back was one of those, oh my God moments. And so then we sent out a whole lot more shells for C14. So we got a pretty good data set. And I think you'll see why we went, oh my God. So Melissa's going to take you through the Betty C data as important implications for where we're for the future, I think, for the Mid-Atlantic.
Okay. So this is all the data from the paper that I submitted to the Holocene that will be published soon. So I'm just looking at the historical biogeographic range shifts and the influence of climate warming or climate change during the Holocene on ocean quahog. So just some quick background information, which pretty much everyone here knows, but ocean quahogs live in the area with the green dots. And as you can tell, that lines up with the cold pools. So their range is dependent on temperature. So as Eric was saying, there was this area offshore of Delmarva where we found only dead ocean quahog shells, which is surprising because obviously normally you have live shells that are in an area that die and produce those dead shells. So we were wondering when those dead shells occupied those areas. So in the past 11,000 years, there's been a lot of different climate changes. So the main takeaway from this is just to say the climate has changed a lot in the past 11,000 years, and there's been lots of colder periods. So our objectives were to determine the timing of the historical ocean quahog occupations outside of their range, where those green dots were, and then determine if the historical ocean quahog occupations coincided with those climate events that were in the previous slide, affected by bottom water temperature. So for sample collection, as we've talked about, they were collected with the Betty C at all of these different stations offshore of Delmarva. So once we collected them, we brought them back to the lab for processing. And like we were saying at the beginning of this talk, we processed them by cutting the shells, polishing, then imaging, and then I took carbon samples. We sent those carbon samples off to UC Irvine, and then they sent those carbon samples back with the results, and we calibrated those with the 400-year marine reservoir age. And I was able to come up with this timeline. So on the y-axis, we have the number of Arctica shells that were dated during the time periods on the x-axis. So this top timeline is before Common Era. And so we have some shells that were dated during the Megalayan stage boundary of approximately 4,000 years ago or 2000 BCE. Then we have some shells that were born during the Neoglacial at the beginning of it and towards the end-ish. And then we have shells dated during the Common Era. So we had one shell dated during the Roman Warm period, some shells dated during the Dark Ages, and then the Little Ice Age. And then we had the majority of our shells that were dated more recently, around the same time as shells that were born for both Kat and Jill's data in Georges Bank and New Jersey. So looking more closely at those more recently born shells, we noticed that the birth years had very similar birth years to Georges Bank. So this indicates that in the southern portion of their range, there was a recent mortality event. So ocean quahogs live outside of their current range during known cold events in climate history, and dates indicate that recruitment at sampling locations in the 1800s coincide with recruitment further offshore and suggest a recent mortality event along the inshore range boundary, presumably due to the movement of the cold pool. And then those earlier radiocarbon dates indicate multiple earlier range transgressions and regressions inshore of the present range, coinciding with those major cold periods, the Neoglacial, Dark Ages cold period, and the Little Ice Age. So the presence of dead shells during those events suggests that bottom temperatures during those times allowed them to live there, and that's what controls the biogeographic range of ocean quahogs. So that just sums up my Holocene paper.
So go back to that, because I want to add a couple of comments. This is good, right?
Oh.
So what happened in the Holocene? Okay, at the end of the Pleistocene, sea level was down something like 60 plus meters. Okay. In the time frame around 8,000 years ago is a period of time called a Holocene climate optimum. And it was during that period of time that sea level came up rapidly. It reached close to present levels between 3,000 and 4,000 years ago. Starting at the end of the Holocene climate optimum, there have been 4 major cold events. The first one, about 4,500 years ago, is this Magdalenian that you see up here. The second one is the Neoglacial, which is order 3,000, 3,500 years ago, something of that sort.
Yeah.
The third one is the Dark Ages cold period. And the fourth one is the Little Ice Age. So we collected along that area inshore ocean quahogs from each of the major four cold events in Earth's history since sea level came up at the end of the Pleistocene. Okay. During those times, ocean quahogs occupied depths at least inshore to 30 meters. And we didn't sample inshore of 30 meters, but the Delaware 2 data set has stations well inshore of 30 meters. So presumably ocean quahogs lived, well inshore of 30 meters, but we don't know that for sure yet. But certainly in this particular region, they lived in at depths much shallower than they do today. The numbers of animals collected does not indicate in any way what the population densities were. What we know from studies of death assemblages is that there tends to be an exponential decay of the number of animals that died over time. So you would expect the numbers to drop off exponentially after death. The fact that we find any out there would suggest from that those were pretty vigorous populations at the time. I think that's a fair thing to say anyway. This is something that has been ongoing, and these animals have moved inshore and offshore with each major climate change. Now, there's an interesting hiatus in here that you should make reference to, and that is that between the Dark Ages cold period and Little Ice Age is something called the medieval warm period. I think we have one shell that fell in that, but effectively there are no animals in any of the warm periods. So there's the one lonely shell for the medieval warm period. There's one lonely shell for the Roman warm period. Okay, there are effectively no shells between the Magellanian and the Neoglacial. There's a warm event in there. So if you look around at where the warm periods are, you don't have any ocean quahogs, which is an issue that we should think about because the world is warming up and we're moving into medieval warm period temperatures right now. And that would be suggested that we ought to be vigilant for a range shift in ocean quahogs. And that we ought to expect it to happen. Okay, so you have more to say.
Yeah, I was gonna start talking about taxonomy now.
Yeah.
So these are assigned Earth years.
Yes.
It doesn't necessarily mean that a quahog born in the Dark Ages didn't live through the medieval warm period at that location, right?
So I aged them and they did not live all the way into the medieval warm period. So I got to see how they didn't live that long.
So all of the shells that you sent for the carbon dating
They were, the oldest one I had was 200. And they, for the most part, they all stayed within their designated climate event.
Yeah, on the next issue.
Okay. And talk about the taxonomy.
Yeah.
Okay. Okay, so when we were looking at these shells that were radiocarbon dating, we noticed differences in their physical appearance. So I'm going to go over that. So taphonic, just a little background information. Taphonic indicators are often used to assess time since death of skeletal remains. So the taphonomic condition of skeletal remains provides limited evidence of time since death in most studies, thereby restricting the ability to sort the temporal sequence of skeletal remains entering the death assemblage. Arctica islandica is a relatively widespread bivalve in the North Atlantic with an extended lifespan, as we know. The usefulness of this species is only limited by the ability to determine the time since death of animals. The age shells that we saw in the last presentation have varying degrees of discoloration and various percentages of remaining periostracum. So the question is, can ocean quahogs of varying time since death be distinguished using those physical differences of discoloration and periostracum? So again, we sampled all these shells from these locations. And we had shells dated between 60 to 4,400 years before current day. And so to determine if a relationship exists between the taxonomic condition and time since death, radiocarbon ages were compared with the amount of remaining periostracum and then the type of discoloration on the shells. So this is just an example of the various levels of periostracum we had remaining on the shells. We have this shell on the left that has almost all of, I guess your guys is right. Or wait. This shell right here that has almost all of its periostracum, and then the shell in the middle that has some remaining periostracum, and then this last shell over here that has no periostracum. And so we categorize the shells by either having periostracum and then not having periostracum. And then with the shells that had periostracum, we estimated the amount of remaining periostracum on the shell. And to do this, we have this diagram over here with the shell broken up into known sections. And each of those sections is a known ratio of that shell. And so I'd estimate the amount of periostracum remaining in that section and then add it up to make the total percentage of periostracum remaining on the shell. And then for discoloration, we had 4 different categories. So we have this shell right here that underneath the periostracum you can see is still white versus the shell next to it has this white, gray, blue discoloration. And then the shell below it has a blue, gray, orange discoloration, and then the shell next to it is completely orange. And we divided all these colors up using color swatches from the Munsell Book of Color with its official colors. So once we did that, this is the depiction of all of the remaining periostracum on the shells through time. So our earlier shells had periostracum remaining, but as you go back in time, you had less periostracum. So all of these shells had no periostracum, and we just had a few shells after 1,000 years ago that had some periostracum remaining. So I fit a GAM or a generalized additive model to the periostracum after transforming the percentages using an arcsine square root transformation. And you're able to see the relationship of, you have an obvious decline in periostracum with time since death. And then this gray area just represents the area fitting those values. And obviously there's more error around the time where we don't have any shells. And so this is a logistic curve of the probability, showing the probability of a shell having periostracum remaining, depending on the time since death. And so you can see the younger it is, the higher the probability a shell is going to have periostracum remaining. And the older it gets, the smaller the possibility of a shell having periostracum. So you have this obvious relationship of periostracum remaining on the surface of the shell to the time it's spent in a death assemblage. And we have a similar relationship with the discoloration of the shell. So we again have a logistic curve going the opposite way. So the chances of a shell being discolored increases as the time since death increases. So you have the earlier shells that have a smaller probability of being discolored, with the older shells almost always being discolored. And again, it's got that logistic curve. And so just some quick conclusions. Our old shells, or individuals that died a long time ago, were discolored orange with no periostracum, while younger shells which died more recently, had their original color, white with some remaining periostracum. And then both the disappearance of periostracum and the appearance of discoloration followed a logistic process with 50% of shells devoid of periostracum and 50% discolored in about 1,000 years. The logistic form of long-term taphonomic degradation is first reported here, as are the longest time series for taphonomic processes and death assemblages within the Holocene record. This relationship can be utilized to triage when deciding what shells to age when you're trying to decide to carbon date, because carbon dating is extremely expensive. So if you can look at a shell and say, this most likely died a long time ago, and you want to know more information about shells that died a while ago, you can pick that shell and you can more effectively select shells for carbon dating. So that pretty much sums up my taphonomy paper. Do you guys have any questions?
So the important thing about this for us in here is that carbon-14 dates are expensive. And I mean, it's $250 an analysis. And if you want to, if all you can do is randomly take animals and send them off for dating, then you're going to spend a lot of money for the information that you want to get back. If you can sort them out to some extent into age groups, then you can be much more effective in how you disperse your C14 money. In this particular case, it's pretty clear that you can do that. The really old animals can effectively 100% be separated from the animals that are not so old. And the periostracum relationship is sufficiently strong that you have a decent shot at sorting out the animals over the last 1,000 years based on periostracum coverage. Now, that is really unusual. I don't know what's unique about the mid-Atlantic continental shelf, but to be able to sort things out that definitively is not common. So we have a particularly lucky thing here because one could, if one wanted to, map out, I think, the regional extent of the cold pool in relatively cost effectively over a relatively large area by collecting shells and sorting them out properly and getting C14 dates. And that would be a game changer as far as climatology is concerned.
I saw Nina raise her hand if you want to ask a question.
Yeah, hi, Alyssa. Sorry, I think I just missed this, but are all of these shells from the same site?
Yeah, they're all from, these are the shells that I just talked about in the last presentation. They're all from off the shore of Delmarva. So they're not all from just one of these sites, they're from all of these sites. But
Okay. Have you done any work to see if it's different between different sites?
it's pretty consistent through all sites. There wasn't, you had sites that had shells from multiple time periods. So you have shells with multiple physical conditions, varying levels of periostracum and discoloration. There wasn't many sites that had like only orange shells or only shells with periostracum. There was one site which, when I publish the paper, or I can give you more information about it later, one site where all of the shells that had that blue, gray, orange discoloration, I think it was Station 26. I'd have to go look back at the data real quick to know for sure. They all came from one site. So that could be something to do with the local chemistry. But overall, we found that all the sites, they had different shells with different physical characteristics. So it wasn't just one site.
Yeah, thanks. That's interesting. I'm just curious because I know in the Gulf of Maine and our sites, we see big differences between sites. Some shells that are relatively recent have no periostracum on them in sort of our northern sites, versus shells in the southern sites have a lot of periostracum that are pretty old. So it's just, yeah, interesting to me.
Yeah.
Thank you.
You're welcome. Any other questions, you guys? Good. You want to talk about growth for Long Island and stuff?
No,
first?
but I wanna talk about something.
Okay.
So when we were out on a pursuit cruise, we collected some surf clam shells where live surf clams weren't found. And that's another thing that came out in the original Delaware 2 study, that there were a very large number of sites where live surf clams were not found, but you did find shells. And we got 2 groups of dates from these. The shells that were collected off of Long Island, and they're all north of Hudson Canyon, but on the western side of Long Island. All dated in the 8,500 to 10,000 years ago range. And those were collected in roughly 40 to 60 meters of water. And at those dates, 9,000 years ago, sea level was down about 30 meters. So they would have been living in something like 10 to 30 meters of water, which is effectively today's depths. So at that time, when sea level was down, that part of the shelf obviously was temperate and not boreal in temperature. But that's not particularly important for us now. What is important is that off of New Jersey, in approximately 60 meters of water, I forget how deep that station was, it was roughly 60 meters, we collected surf clam shells that dated to the medieval warm period. Now that region would have been at present day sea level, more or less, at that time. That's considerably deeper than the pursuit found any living surf clams in the region in August. And it would suggest that during the medieval warm period, the cold pool, as far as being off the coast of southern New Jersey, the cold pool would have disappeared. Or at least there would have been remnants of it deeper than 60 meters. So if you utilize this information to look at the future with respect to the overlap issue, the take-home message is it's not as warm now. It's not as warm yet as it was during the medieval warm period. But we're moving in that direction, and you see that with the surf clams. And one can expect that that in some years in the future, however many it might be, that there will be fishable concentrations of surf clams at least as deep as 60 meters. And the ocean quahogs will have gone away. Now, I don't know what the timeline is, but at the rate things are warming up, that's probably a 20-year projection rather than a 100-year projection.
What was the year when you're on the medieval warm period? What's the framework of the years?
It's roughly 800 to 1200. Right before the Little Ice Age. The medieval warm period converted to the Little Ice Age, apparently in less than a century, right around 1300, plus or minus.
Mm-hmm.
Did I misunderstand what you first said, though, Eric? Is that the shells you dated were back 8,000 years?
So there were 2 groups of shells. The shells off of Long Island were all in 8,000 and 10,000 years ago range. Surf clams. And that's when sea level was down. They would probably have been living at the depth that they're fished now. And likely that temperature, because they're nice big shells, but of course, that would be much further off the present shoreline than today.
Okay. So when the argument you're making about ocean co-op overlap has to do with the surf plan locations and the warm
Yes.
and not that 9,000 years ago.
Yep.
If that was true, then there'd be an interaction with depth and
Yeah, no, this is with sea level up. The difference between now and 1,000 years ago is a couple of meters. It's not much.
Right.
So, and the temperature range would have had to be consistent with the generation of, nice large surf clams, which, is a cool, temperate, and not a cold pool temperature regime.
This is just the timeline that Eric's talking about. These are the shells that were born around year 8,000 BCE, and then these are the medieval warm period shells for the Atlantic surf clam. And then I can show you where we sampled them, and we got them from these stations. Just so we have a visual to go along with that.
So now you're up to date on historic range shifts, which have been going on a lot in the past. You didn't have one to talk about when these animals died, right? You have a slide?
Their growth period.
You have that in the growth rates?
I don't have exactly when they died, but if you look at the growth presentation, we
Oh,
talked about how it shows.
We'll wait for that.
Yeah, how old it's.
We'll wait for that.
Okay.
So we're now on to growth rate, right? Am I correct?
number 7 and number 8.
Yes, we're going to come back to that. I'm going to jump over that.
You want to go 9 and 10 then?
Yeah, because I want to definitely, we need to spend some time on growth curves. So we need to get my presentation up, however you might do it.
So. I'm assuming it's
This is
growth.
when I proved to Tom that these animals are not equilibrium now.
With the environment.
Okay. So when you age animals the way Jill showed you this morning, with the software that's involved, and remember, she put little blue dots on each of the things. The nice thing about that is the software doesn't simply just count how many years there are, but it tells you the distance between the blue dots, which is the growth rate. And so for each shell, you get a growth curve out of that, automatically, without having to do anything else except just hit go. So we have lots and lots and lots of growth curves. And Kathleen did quite a bit of work on what the growth curve equation should be. So this is Georges Bank and Long Island. Males on the bottom, females in the middle, total population at the top. First thing to note is that the line with the large dashes is the von Bertalanffy fit. And I think you can convince yourself that von Bertalanffy will not model the growth of ocean cohogs. It underestimates L infinity by a great deal, and it has a problem near the bottom of the plot because ocean cohogs have a little bit of an S shape at the bottom. So you can throw von Bertalanffy out, it's useless. What do you use? Well, the key thing is you need a growth curve which allows the length to continue to increase over time, which is a very atypical growth curve. Almost nothing that is a single organism. I mean, corals kind of do this because they continue to grow and grow and grow, but they're colonial animals. For animals that are not colonial, not having an asymptotic growth is pretty strange. Quahogs don't, they clearly don't. There are two options for this. One is the Tanaka curve, and that is in the middle there. It has 4 variables in it, or parameters in it, cleverly named A, C, D, and F. I don't know what happened to B. Invented by a fellow in Japan some years ago for a bivalve called Laternula. Some of you know Laternula. It's a common bivalve in polar regions. Not used after that for bivalves that I'm aware of. It has been commonly used to model sea urchin growth. It clearly fits much, much better than Tanaka and then von Bertalanffy. It underestimates largest size. If you have old animals, it consistently underestimates largest size. There's a modification with an additional term, cleverly named G, that fits older animals better. So the best curve to use is the one that has 5 parameters in it. This particular fitting this curve, we learned, unfortunately, actually, but you have to be careful about negative numbers. Both the Tanaka and the modified Tanaka have logs and square roots. And inside of those, of course, you can't have negative numbers. And as a consequence, you have to make sure that A, C, F, and G do not go below 0. So you got to pin them at 0 when you're doing the curve fit. And it will find negative numbers for some of these. If you don't do that, those are mathematically impossible results. So you have to pin those at 0. The lower number, the lower bound has to be 0. Kathleen did both an AIC and a BIC evaluation. The modified Tanaka wins. It's modestly better than the Tanaka, and you can throw out any of the other growth curves. I mean, she's looked at von Bertalanffy, but it doesn't make any difference. There's a whole host of growth curves. You can throw them all out. None of them are going to fit, come close to fitting ocean quahogs. So among other things, a very strong recommendation would get somebody to grab the thought and tell him he's got to put Tanaka into stock synthesis.
We currently have a couple of things that might work. One of the features is that the Bornberg fit can start at a linear below that. So the left side of your curve, I think you can get pretty close with just starting the Bornberg curve that was 15. And then for the rest of it, he's allowed the option for K to be different for every age. So you could potentially set your L infinity at some value that's above the largest observed animal, and then have may gradually decrease. Which would approximate the non-acid products.
As long as you can get close to something like Tanaka, because it has to have those attributes.
I don't know that it would estimate that. I mean, there's so many ages where estimate.
I mean, it would be a whole lot better just to stick this thing into stock synthesis.
Yeah, I mean, it does stuff like this all the time. So if you know, call them and say, hey, your model's garbage. I'm not super happy that we change it so often, so I don't like to encourage them to do this, but every time you turn around, there's a new version of it. You have to change some stuff.
So, you know, the issue, the other issue that we've discovered, which would be obvious to you too, is that if you don't have an old animal, you don't get a good fit for the parameters that are controlling the long upper slope, right? Like G and D, those wander around in sort of an odd way if your animals are only maybe 30 or 40 years old or something. So you have to take that into account. So getting an individual growth curve for all of the individual animals, some of which are young, is a little problematic. But if you have a group of data, the way Kathleen has here, you know, you can get an average curve for the population or the sexes pretty straightforwardly. And she has a curve fitting routine in R that does this. If anybody ends up wanting a copy of it, she's got that set in R. So
We also have something in there for tuna called growth cessation. I think it's fairly flexible. It allows for changing growth rate after maturity. So I think you can get it to, you know, be linear, then grow at one vertical amphi, then hit some fictionalized maturity, and then slow down. So
I still think the way to make this simple is just get Tanaka into stock synthesis. There's no question that it fits really well. Okay, I mean this is the growth curve that ocean cohogs work on, and we ought to just do it. I think.
Somebody's gonna have to figure out a trend. But I don't think that's somebody smart to do that.
So the other thing that Kathleen did was look at the growth rate for various cohorts, and she divided things into, generally speaking, 20-year intervals. There's a few longer ones because of the more limited information further back in time. But at any rate, again, the big dashes are all von Bertalanffys, and you can just see how terrible they really are. So the Tanaka and the modified Tanaka tend to work pretty well until you get beyond the data. They don't extrapolate very well. You know, the nice thing about von Berts is if you have enough information to get you up to near L infinity, it really is a curve that you can extrapolate out. Yeah, or it doesn't change much, or it gives you a decent guess. The Tanaka won't do that. You know, once you get to the end of your data, that's just about as far as you're going to be able to take it. But of course, most of the time, that's all you want anyway.
previous. They perform differently on the smaller.
Not really, no. They've almost the on the lower end of the curve is controlled by A, C, and F. And those are the same essentially in the two. The D and G control the right-hand part of the curve. Von Bert's the one that can't do it. Yeah. And you know, I showed you earlier on this morning that the tendency for the first few growth years to be shorter than the next few years before they really start to decline again. There's a definite S in ocean cohogs. I mean, it's not extreme like you might find a few other species where, you know, like we might use a Gompert's fit or something, but there's a definite S down there. And if you do the derivatives, you find out that the fastest growth rate is not at the first growth rate after zero. For Von Bert's, it is. It's the very first growth rate. It's the fastest growth rate. But that's not true for the Tanaka formulation. Here's Long Island. Same story, same outcome. No problem doing fits. Now, we tried a bunch of ways to look at growth rate changes over time. And one of the ideas was to use the derivative for the identify the fastest growth rate from the derivative and plot that. For a number of reasons, that tended to not work really well. And one of the reasons is that it's not intuitive. So we decided to take to do the Sarah Pace approach and say, you know, how long did it take an animal to get up to 80 millimeters? Saying 80 millimeters is basically the size that's fully recruited to a commercial dredge, right? So how many years did it get to take up to that? How many years did it get to 52 millimeters, which is approximately the 50% maturity line? And that number comes from Iceland work. And the presumption is that maturity is somewhere around that for our ocean cohogs. So we've taken a look at primarily at those two sizes and the time required to get to those two sizes. So here is growth rates for George's Bank, I think, in millimeters per year. On the right are the actual numbers for each of the time slices that Kathleen used to calculate the average number. Most of these are 20-year time slices. Some of them are a little bit longer. The left hand is an exponential and a linear fit. Obviously, linear doesn't work. Exponential is better, but it's not great. The modified Tanaka models produced comparable growth results as the true age data, which again reinforces things. Now, she doesn't have up here, unless I can't see it, but on the right-hand three plots, the solid line is the George's Bank data, and the dashed line is the Long Island data. And if you look at the top one, which is D, top right, which is D, this is the growth rate that comes out of this calculation for animals getting up to that maturity size, which we said was 52 millimeters, okay? And if you look at that, it doesn't take very long to observe that they got up to 52 millimeters a whole lot faster in 19, what is that number? 1960? I guess it is 1960, then in the late 1700s. And that's true for both of them. The differential is pretty impressive. If you look at the dashed line, they're going from something like 1.5 millimeters a year up to something like 3.75 millimeters a year. So it's more than double. The growth rate is more than double in 1960 relative to 1800. The middle one, which is E, is how fast it gets up to 80 millimeters. And again, you see this enormous change. And for Long Island, you go from somewhere around, let's say 0.6, and excluding that really high one at the very end, just because, you get up to somewhere around 1.3. And again, that's about a doubling. And Georges Bank has increased also, but not as fast. Okay. So in both of these, you have a situation in which, in the Long Island site, a huge change in growth rate since the Little Ice Age, and a somewhat more muted change in Georges Bank. And in fact, the growth rates for Long Island and Georges Bank at the end of the Little Ice Age were very different. And by the time you get up to the latter half of the 20th century, the growth rates have come much closer together. So Georges Bank has been moderately changing its growth rate over time. Long Island has changed a lot over time. We know, if you look at the cold pool data, and Kathleen's Long Island site is on the inner edge of the cold pool off of Long Island, that region of the cold pool degrades early in the fall. And as a consequence, that part of Long Island is warming up faster than other regions in the cold pool. And that would be consistent with this huge change in growth rate. So take-home message on growth rates from that plot. What's the population growth rate? Because, we use growth rates a lot. And the growth rates come out of the Tanaka curve or the von Breuck curve or whatever, okay? So what's the curve for the population? Well, there isn't one, right? There isn't one. There are growth rates for the cohorts, but is not a growth rate for the population, which is why they're never at equilibrium. Oops. Jill, do you have some stuff on this? Okay.
Yeah, so we'll just take a quick look at my growth curves and see how the Tanaka and von Breuck compared in NJ1 and NJ2. So we'll look at NJ1 first. Interestingly, all three models seem to fit the population pretty well. The Von Bert doesn't really extend as far or as quickly as compared to when it breaks down into male and female. But the Tanakas are pretty similar across all three levels. Interestingly, for NJ2, the modified Tanaka, I'm not sure if this is it becoming unstable or if it's just predicting it out to be a really large age. But again, here the Tanaka does fit the best. Von Bertalanthus is pretty much, I don't want to say the worst, but it doesn't really fit all that well. But if the modified Tanaka is correct, and if it's not becoming unstable, then it would think that NJ2 has the ability to grow to overall sizes larger than those seen at its northern counterparts. But we don't know that for sure. Interestingly, here's just a direct comparison between NJ1 and NJ2. And NJ1 is smaller than NJ2 and will be predicted out to be smaller than NJ2. Nina Whitney says goodbye.
I think Eric said the fit was being evaluated.
Repeat that question.
The question was asked if this was still the fit here was still being evaluated by the AIC, and the answer is yes.
This is a suggestion for, I like to see fits like this as part of the residuals. Again, it's hard to tell with a curve by eye where things are biased, and you kind of tell it. A lot of times just residual plot nice, or else alternatively you do model prediction against the data. One-to-one. It's just easier to look at a straight line and see where you miss than a curve.
Okay.
For what is going on.
Okay, so the last thing we'll look at is NJ1 versus LI. I'm sorry that the Long Island one is a little bit blown up. I tried to make it fit the best I could with what Kat had. But they are pretty similar. As we saw again with our age frequencies, we're seeing that the growth curves are pretty similar as well. So there is high levels of similarity between these sites, and they are our two closest sites. So that's what we would expect. I haven't done the cohort analyses. That's something I'll be working on within the next few weeks. I also need to analyze the time to maturity, as Kat did.
Can you go back one slide? At some point, Eric, is it valuable to study what the conditions in New Jersey 2 might be that projected standard growth rate in the old age would be different? Would it be food source? Would it be temperature? Would it be? I mean, maybe this is not accurate, but it just looks to me like the thing would continue to grow and grow and grow, whereas the other places it seems to level off.
Yeah, so Guy asked to compare these two. The question is the projection of growth at NJ2, which seems to indicate that the animal is going to continue to get larger and larger, and NJ1 seems to level off, or the rate of increase is less. And again, the point I would make is that in the Tanaka business, any extrapolation beyond the data is, I think, completely invalid. There are a lot of parameters involved in this curve, and you're asking all of those parameters to get projected into the future, and it's just looks to me like it's a highly unlikely to be correct. You just have to stop it at the end of the data. Okay.
Yeah, I suppose you could do that on pictures.
Yeah, that's what you would do.
Yeah.
And let's add some info.
My info is also a work in progress, so take that as you will. This is the last chapter of my thesis that I'm currently finishing this week. So
These are so-called fossil shells.
yes,
Maybe use the term fossil.
the dead shells. Wants to load. Okay. So start from here. So because both Jill and Kat pretty much agreed modified Tanaka is what fits the best, I just went with the modified Tanaka. So these are all my shells that were born overlapping in that modern time period at the same time as shells from Long Island and George's Bank. So I was able to do a similar cohort analysis like Kat. So my oldest modern shells were born in 1740, and I was able to compare their growth modified Tanaka growth curves to George's Bank and Long Island. So you can tell my shells from Delmarva grew more. And you can see that pretty much throughout all of the time periods. And so I can compare in 1760 to just Long Island because Kat did not have George's Bank data for this cohort. And then in 1780, again, you have my shells from Delmarva with a higher growth curve. Again, 1800, and throw out all of them. My shells in 1940, actually, they were born at the very end of that cohort in 1955, between 1955 and 1959. They were pretty young, so I would not say that the modified Tanaka was the best estimate for their growth, but that's what it could do with the super young shells. Yeah, I think the biggest takeaway is that further south, you have this faster growth curve. Yeah, from 1740 all the way to 1940. And obviously, disregarding this crazy curve, if you just look at the raw values right here, this light gray down here in the 1940s, you can still tell that they're further above Kat's, Long Island, and George's Bank.
And we don't have any live data for down
No, no, these are, yeah, they're all dead now, so.
No, I mean, even offshore. Your shells are further south than Sarah's station.
Oh, yes, that's what you mean, yeah.
We don't know anything about the growth curves.
Yeah.
The live animals.
It'll be nice just to see Jill's cohorts on top of these to see if they fit somewhere in the middle. As you go further south, things are growing faster. Hopefully. And so this is just so I can compare my older growth curves to Kat's population growth curves at George's Bank. Yeah.
So one of the questions that I was interested in is when these inshore animals die.
Here. Oh, okay. Yes. So you can see.
You can repeat my question.
So Eric is interested in when my inshore animals died. And so if you look at the shells in 1740, it's kind of hard to see right now without zooming in on individual plots, but my oldest shell died about 200 years later. Or sorry, like 100 and almost 200 years later. And then again, you have in 1760, most of the shells in 1760, and that 20-year cohort, which means they could have been born anywhere between 1760 and 1780, only lived to a pretty young age. I would say like 20 something. But yeah, and so this kind of gives you a general idea of when these shells died.
So in the cases where you have a reasonable number of animals,
Mm-hmm.
which would be 1740, 1760, 1780, and 1820, if I'm looking at things right.
Yeah, it's
At
easier to
least-
see when you zoom in
at
on
least
each plot.
in 3 of those cases, in 1760, all of those animals died, very early.
Mhm.
But for the other 3, it looks to me like the estimated death dates are in the early to mid 1900s.
Mm-hmm. Approximately.
So you don't have any animals that, for example, the first survey down there would have been roughly 1982 or 1980.
Mm-hmm.
You don't have any animals in your collection that were probably alive at the time of the first survey. So that mortality would have occurred prior to the survey,
Mm-hmm.
which is one of the reasons why we didn't find any live. In the survey data, there's no live animals reported from those areas, right? Because they had all died by that time.
I don't know if you guys on Zoom can hear Eric, but basically he's saying that if you look at the ages of all my animals, they basically died before 1880s, which is when they start 1980s. Sorry, talking about too many different centuries. But they died before 1980, which is when they started surveying. So they wouldn't have found any live shells in the region where we found all of my dead shells when they started the surveys. Okay, so moving on.
And if you go back again, and you can do this, but it looks to me like a lot of those death dates are around 1940, plus or minus maybe 10 years.
Yeah, I'd have to look at them
And that
exactly.
would have been the last warm up prior to now.
Mhm.
The last, and we don't have any cold pool data, I don't think, for that. But presumably there would have been one of these heat wave effects in the 1940s
Mhm.
that might have resulted in that mortality.
Yeah, I would want to go back and look at all the exact death dates, but yeah, I agree. Okay, so then if you guys remember my previous presentation when I was talking about all the older shells that were born not in that more modern time period, but more historically, I was able to create growth through time with them. And so I just had Kat's curves right here just to know what, so you guys can compare those to the modern curves. I will at one point actually put those curves on here, but like I said, this is a work in progress. I'm finishing this week, so those will be added on soon. But when I put all of those shells from that those cohorts in the 1700s and 1800s, 1900s into just the modern time period, this is the growth curve that I'm able to create. And then we have the growth in the Little Ice Age. We only had that one shell in the medieval warm period, so this is just the growth for that one shell. And then we have the growth of the shells in the Dark Ages. Again, there was one lone leaf shell in the Roman warm period, so that's all based on one shell. And then I broke the neoglacial into 2 different time periods, and then you have this growth curve for Neo 1, which is the one that is closer to today, and then the older section of the neoglacial, which is Neo 2, and then that Megalayan stage boundary, which is the oldest shells, or they died the longest time ago.
So one thing that would be great on these graphs, I mean, it's easy when you see that when you have one shell.
Yeah.
But it's good to have the sample sizes.
Yeah, no, I'm planning on adding that. Just like a little n equals.
Yeah.
Yeah.
But these do not have Kathleen's curves on.
No, they don't have, I'm going to put those curves. I just haven't had a chance to, because I made these curves this last week. So I just haven't had time to add her data. I don't have her curves for overall population, just those cohorts. So. So then I just have a little tidbit about a scam that I ran with temperature versus growth. So this was with Kathleen's data from Georges Bank and Long Island. So I created a GAM with temperature and age as predictor variables, and then growth as a response. And so you can see age had the biggest effect on growth, which we know.
What were you using?
Between 1958 to 2017. Because that's 1958 is the furthest time we have back with the bottom temperatures. And those are the temperatures that I got from Vincent Saba. And so it's kind of hard to tell because it's such a small difference in growth, but all those older growth increments are pretty small. As you can tell, it goes down with temperature. So growth decreases with an increase in temperature, which supports the idea that we're going to have an issue with the climate continuing to warm and shifting the range of our ocean quahogs because of it.
Is that temperature by itself not accounting for the age?
This is, it is accounting for age. Yeah. If I take out age and I just do growth equals as temperature, you'll see age accounted for in the max temperature. Yeah.
So the important thing here is the important thing here is that growth is slowing down with increasing temperature.
Mm-hmm.
So the data go back to 1958. So the first decade or decade and a half of that time series is a cold period. It was 1960s were the coldest period since the 1920s. So, and then beginning in the late 70s and early 80s, the world really started warming up, and it took a big uptick around 1990. And starting in the early 2000s, we began to have what is now being called heat waves in the ocean, with yearly events that were dramatically warmer than other times. So, and you use both Long Island and Georges Bank.
Yeah, together.
So these areas, you sort of tend to think about animals growing faster as it warms up. And in Kathleen's data and that you saw, going all the way back to the 1700s, there's no question about things growing faster as you warm up. But for our region now, it looks like we've gone over a hump, and growth rates are now going to be declining as it warms up because it's too hot. And the consequence of that is to inhibit growth. So that looks like, I mean, that would be the inference from Alyssa's data that in the Long Island to Georges Bank region, we've crossed a physiological threshold from the area where growth responds positively to increasing temperature to an area where growth responds negatively to increasing temperature, which of course would be the case had we been wise enough at the time to look at it, that we would have probably seen off of the inshore Delmarva in the late 1990s. But we didn't know at the time that what was going on was what was going on.
So you're using max temperature here? Is that the max temperature at the location that time was collected, or its entire lifetime?
No, it's the max yearly temperature during that year. So the max temperature for that year of growth.
And the growth is incremental for that.
Yes, yeah. So each growth is matched up with the year of growth and then the temperature for that year.
Okay. Anything else? So I have one other thing to present. Have you done everything? How do I go to?
Your presentations.
Yes, I need to open up some of the PDFs.
Okay, do you any particular? Do you want me to open all of them?
Yeah, all of the ones that are just PDFs.
Eric, if you're interested at some point, I can tell you, I just reviewed a red drum stock assessment. Where they had, that's a weird fit that seems to go.
Oh, yeah?
And partly because they don't really have.
So I've got one little thing to say, and then we'll do that.
Do you want this model?
No,
open?
not
Okay.
model.
Okay, so
So I just
You want
click
me
up
to-
here.
yeah.
Now I can click up there.
Okay.
Do I use this?
Yeah,
Or-
either or, whatever your preference is.
Okay. So one of the problems looking forward, if we want to do age frequencies, is to ask the question, how many animals do I have to age? Now, this is a work in progress, and I've used the data set that's the most well-behaved, which is George's Bank. And if you remember, George's Bank doesn't have a little hump of little ones at one side. It has a relatively short tail at the other side. So it's a nice, well-behaved age frequency. And I started with this one with the idea that if I can find something that works here, it's probably going to work everywhere, or at least I'll learn something. Then I can go to the worst places. By the end of the summer, I'll have the worst places, but life's rough. I don't have them yet. But and I've been looking at males and total population. Haven't done the female plots yet. Arguably, I should have probably been looking at females rather than males, because females obviously are better behaved in a whole variety of ways. But nonetheless, I have learned a few things with respect to how many animals you need. So what have I done? Okay, I have extracted from the present, in this case, male size, age frequency data set, a series of pseudo data sets based on a certain number of random draws in each age class. So on the x-axis, or I'm sorry, the x-axis is the number of random draws for a particular length class. So 5 animals out of each of the length classes, if there's a 5 down there. And I've utilized that information to generate an age length T and then an age frequency. And then I've compared it to the truth, which is in this case, Kathleen's age frequency, which we're declaring as true. And then I asked the question, are they different or not? And I've used the standard tests. Now, Kathleen aged about 300, a little over 300 animals for her male age frequency. Okay. So the y-axis is the number of animals aged. And in the Kathleen data set would be at 300. Okay. Now, in this case, this is the KS test. The dark lines are the ones that are the raw data comparisons. The open symbols are the ones with the compressed tails to remove the size groups that have, or age groups with only a few animals. Okay. And I've put the 1st percentile, the 5th percentile, the 10th percentile, and 25th percentile. Now, the take-home message is that I've arbitrarily said, I want to know when, if I take 50 or 100 or whatever simulations, when the probability of a significant result under a particular percentile definition drops below 10%. So I'm willing to allow 10% of the draws to be significantly different at that level. But I want to get it down below, at or below 10%. So here is the 10% line right there. Okay. And I get below that right here for the highest percentile. And you know, the 25th percentile, I mean, that's most people would never use anything above 0.1, p-value of 0.1. This would be a p-value of 0.25. Okay. So I'm being kind of persnickety about having them be similar. I drop below that right here, which is a number of animals aged of 200. So Kathleen aged 309, I believe, or something like that. What I would say in this particular case is actually she didn't have to age that many males. She could have gotten away with 200 of them if they were equivalently dispersed properly across size classes. So we oversampled the males with respect to the KS test. Now here's the Anderson-Darling test, which is the tail business. And now, of course, the 25th percentile is ludicrous because they're always significantly different. So I've dropped back to the other one and said, well, this is this first percentile condensed is the least stringent requirement that I could make. And I'm going to ask, when does that drop below 30%? So 30% of the runs are still significantly different, right? And that occurs right in here. And with a number aged of 360, which is more than Kathleen aged. So the take-home message for the males at George's Bank, if I am concerned about the center part of the distribution, and I'm going to use the KS test, and that's sufficient for me, I actually don't have to age 300 animals. I could get away with fewer. If, on the other hand, the problem that I have has the requirement of having a reasonable tail specified, then I have a big problem with 300. I can't, it gives me nonsense almost. And in fact, if I want to get that below 10%, the most string, and this is the first percentile, 0.01 p-value, okay? I'm going to have to age at least 440 animals from this site. So I pay a big penalty if I want to stabilize the tails of the distribution. On the other hand, if all I want is the part of the distribution where the majority of the animals are, then I can get away with less effort than Kathleen put into it. I can do this also for the entire data set, not just the males. And since the males and the females obviously have different lengths, I would be worried that I might pay a penalty by combining the sexes. Now here is the KS test. Here's the 10th percentile. And I dropped back down below the magic line with a number of animals of about 200, which is about the same as the males. So going to the whole population and not sex specific, I've effectively paid no price as far as the KS test is concerned with respect to that. And the interesting thing about this is, because I also know the age frequencies are the same, if I'm willing to not push the length data too hard, I can get a good age frequency and just looking at the females, and I don't have to age any more than I would for the whole population. But I get a much better idea what's going on in the female data set. So that's a good thing, maybe. Here's Anderson Darling. This drops below the magic line right in here for the 1%. And yep, right here. And if you look at where that is, 900 animals. So if I go to the population end of things, I don't hurt myself where most of the animals are. But the tail becomes a whole lot more erratic because we know that the males and the females are differentially proportioned in the tails. And by putting them together, I add variability into the tails. And the consequence is now I have to age a whole lot more animals. So it depends on what you want. But if you want to minimize the number you need to age, you probably want to focus on one of the sexes, and you know you're going to get the same age frequency, more or less. That would be my interpretation. Now, here's a word of warning. What if I measure the lengths on the boat, and then I bring the clams into the lab, and I measure the lengths of the clams in the lab? And I have to do that so I can calculate the pixels if I want a growth curve and stuff. Okay. And then I have now the age and the length of this animal in the lab, and I want to apply this data to the field. And what if I have a measurement error where the measurements are a little off between the two? And for grins, I made this measurement area 3 millimeters. Now, I don't think that's ever going to happen. I think a differential of 1 millimeter is very likely. 2 millimeters is, right in there. You could see it. 3 millimeters is probably not likely. But what if it was 3 millimeters? Okay. This is the KS test, which, remember, is very well behaved. It's a total mess. Okay. I would have to, I would have to age thousands of animals to fix this problem. So there's enough variability in age at length that if you add the variability of having a mismatch in lengths relative to the ages, you will end up with a complete disaster, which means that if you're going to do this, you have to have real tight control on the accuracy of the lengths on the boat and in the lab, or you will end up with nothing. That's an absolute certainty. Now, I tried a couple of things. So I thought, what's the real problem with age at length? If you look at the distribution, okay, in a given size class, okay, typically it's going to be right skewed. I've got a bunch of younger animals and a few older animals. If I look at the variance, typically the bigger the size class, the more variance is going to be in there because there are larger dispersion of ages in that size class. So the variance is different. The number of old animals. Let's say I say, how many animals in this size class are older than 150 years? The number of old animals in the size class is going to increase in the upper relatively large size classes, okay, because you're pulling in more and more old animals, but you still have the young ones sitting in there. And I can look at, or I could look at how, what the age range is in the size class. Because the complicated, irritating size classes are going to be the ones with the largest range. And so can I play a game by saying, if I know this for each of the size classes, can I age more 100 millimeter animals than 80 millimeter animals? Because I know the 80 millimeter animals have a small range in ages and I don't have to age many of them. The 100 millimeter animals have 200-year range ages. So I have to age a lot of them to find out what that distribution is. Can I play that game? Now for George's Bank, and so what I'm going to do then is I'm going to age a few animals from each of the size classes, generate this metric, skewness, variance, whatever. Now I'm going to use that to apportion the rest of my work. So the size classes, for example, that have the highest variance, I'm going to put more effort there. I'm going to age more animals there than I would in another size class. Okay. So I can play that game. And then I can ask the question, do I win? Can I do this with fewer animals? Okay. And the answer is, for George's Bank, it's pretty hard to win. Okay. So here's the KS test, where I have done this. And the way you can read the x-axis is, I started out taking 10 animals in each size class. I declared that in the worst size class, I would age another 20. So I would have 30 from that size class. In the best size class, I just keep the 10 and not worry about it, okay? So that's what 1030 means, okay? And it turns out, for KS, and here's the 10% level, this one drops way down, but it's consistently down. By the time you get over here, that value is about 220 or 30. In the original way where I aged everything equivalent, it was about 200. So I don't get anywhere with KS. If I believe this one, I'd be right at the 200 again. So I haven't made any progress with KS. That's a little disappointing. Here's Anderson-Darling. And now I'm going to look at this guy. And now I'm up here, and this is around 320 or 310. In the previous case, I was up around 360. So I've played this game with Anderson-Darling, and actually I've gotten somewhere. Now I haven't halved it, but I've generated a better outcome with the tails of the distribution than I had previously by moving my effort around the size classes, and yet I get a better outcome, or at least as good an outcome, and I've had to age less. This is more effort in the size class with the largest age range. Okay. That's right. So in this particular one right here, for example, I took 30 animals out of each of the size classes. And then I took up to 20 more animals depending on the age range, which is actually one of the games that Sarah played in her paper. If you go back and look, she chose some size classes that had a particularly wide range, and she aged a few more animals from each one of those. And it was pretty clear that it improved in her case, but she undersampled as a whole, okay? So now I have to do more. I think when I go to something like NJ2, which is a particularly aberrant age frequency, I'm going to find out that I'm going to get further playing this game than I did with George's Bank. because this is the most well-behaved one anyway. And so I should have less ability to make it better, I think. But the point is, there's a possibility, and by the end of the summer, I should have this done. It takes half a day to run one of these simulations, so it's not a fast thing. I should have some guidance if I'm going to go into the age frequency business. What are the things that I can do to minimize the amount of time in the lab? And it looks to me like the first thing is get rid of the males and just use the females. That's the first thing. Then the second thing is there's going to be some combination of initial ages and additional ages that'll bring that number that you need to do down some from what it would otherwise be if you aged the same number in all the size classes. But if think about it, you're not going to get this down to like 50 animals, right? I mean, we're talking about for any particular age frequency, just for the KS test, which is the best behaved one, you're really going to be in the 150, 200, 250 animal range in order to do it.
Based on comparing true age frequencies.
That's right. That's right. And I just count how many are significantly different at a given level. And then in the AD case, I just arbitrarily said it's a home run if fewer than 30% of them are significantly different. That's just picked out of whole cloth. For the KS test, 10%, and I also use different percentiles. Okay, so it depends on whether you want the tail to be good or not. Basically, that's a decision up front. If I don't care about the tail, I don't care about catching and accurately describing the oldest, let's say 15 or so % of everything that's in there, then I can dramatically lower the total number of animals that need to be aged. And I'm going to drop them out on both sides, right? So I'm dropping out the really young ones, and I'm dropping out the really old ones when I do that, because the tail gets compressed on both ends by the same rule. Now, I think that's the last piece of original data. I don't know if you want to look and see if there's anybody on the chat or something. I can get rid of that.
Yeah, no one said anything on the chat.
You want to take that off and let me get the agenda back up. So do we want to take a 15-minute break and then come back and go through some of the questions? Because I mean, it's a possibility we could finish today. I don't know. This depends on how much discussion is going to be. But I do want to put some questions and points out for discussion that I think are important. And we want to make sure we're getting guidance back to our board members about where we are now and what we might need to do in the future, or are we done and can we go study something else? We really need to get that kind of feedback, even if it doesn't happen today and you think about it over the next little while and send something in. But somewhere along the line, we need to have an evaluation of where we are with respect to where we ought to be. So 15-minute break and come back. Which would be what time?
So 3:40, yeah.
3:40?
Yeah.
Well, you can always write us an email. Because we do need your plan.
Yeah.
It's good standing.
Do you have the questions actually written out on
Well, in essence, if you go through, because there's some places where I say, what about this, what about that? Okay, and the first one, I think it's number 7, because we skipped over number 7, so we're going to start at 7. And there's some basic questions. The most basic is, are we going to stay with length-based assessment?
Same month. I think it's pretty straightforward there. Train.
Yes, Sarah mentioned there was a little like going away party.
But I can't.
Saturday?
Not this Saturday.
Not Saturday.
Next Saturday. I think that's when I'll be going auction. A little bit. Really nice.
No, razor.
Yes, I drove up because I lost the dog, and so I brought her with. And then as we were driving up, we saw a adult staying playing at my shoes on.
And just the dates later in May didn't work out. So they just actually
On my list, concerts to go to. And Mom and I were
Yeah.
3 times. And we had, not yet.
I think it might be kept down.
No, they weren't.
They weren't. So I was like,
Well, again,
you can't use
but
them.
we had tickets for his musical,
You can have them.
April 2020.
And then
Canceled.
COVID.
So yeah.
Yeah.
Ugh.
That'll make me happy.
There's 2 nights.
Yes,
I think it's a little bit. But yeah,
it's worth it.
yeah, right.
And I'll
It's
probably
gotta
go
be
on
last,
that.
it's gotta be his last tour.
Who knows? I just heard he's gonna produce the album.
Oh, really?
Yeah, but he's not saying that.
Yeah, well, I mean,
Worth it.
Yeah, when it's in the neck of the woods, it's like food tour. So,
Okay,
it'll
yeah.
be camping,
Doesn't.
I haven't been there.
Okay, yeah, that's a
You
good
were-
one.
you were-
We finally got the board.
I think that,
And they, not always came in.
yeah, I think the amount of things are.
I think we gotta take care of.
Well, that's coming up.
Okay.
She's been doing it with surf plants.
Yeah, she was showing me how to, originally I was doing something similar to her. She showed me her
Oh, you guys were.
mixed linear models. Yeah, so I was doing stuff with that. But then I was talking to Saba and he thought again would be better because he didn't like the assumption of renewable.
Sure, yeah, it's, and it probably isn't, right?
But it gave me, when I was doing the mixed linear relationship or the mixed effect models, it gave me the same negative relationship.
Right, right.
Just,
Yeah.
like, so.
With Sarah's model, she
Hi,
needed
I
to
discovered
see
how,
like
how
shift
brain.
and our
Okay.
younger age is actually
July
grow
23rd.
better than the adults. And then as they age, that's when it starts to shift.
Okay.
Yeah.
Okay, yeah, I'll have to look at hers again, because she was so, I was talking to Daphne, she was telling me about
Oh,
her.
I know, like what the schedule looks like.
Oh, yeah.
Yeah, I was giving her models. So
Yeah.
they
That-
sign off originally, but then you more data
That-
science.
Yes.
Yeah.
We ought
Was
to,
that
you know,
originally?
talk about it.
Yeah, well, but Sarah also gets really, you know, with different seasonal, sometimes like summer statistics rather than just the highest temperature in a given
Is that the
year.
one with kind of marble?
When we were looking at,
Matt?
it's hard to, you're only really have the one.
Oh, really?
Well,
Earlier one day.
no, okay, so you do the fall, okay.
Yeah, I can do it.
But when we were looking at the different seasons,
You gotta check
we
your-
found the maps.
Well, can I pull up the website of the research? Because I think I was originally thinking one and then I stopped it. Sometime last week when we were updated.
Yeah, yeah, I mean, I'm assuming the fact that temperature doesn't affect that much.
Yeah.
That's been with us.
Or it's really, really just.
Yeah, which
extreme.
one program
Warm
is
temperatures.
extreme, yeah, that one was, yeah. I agree. I wish we had temperatures going further back, because there's so much data.
Mhm. Yeah. With the surf plants, it's the opposite. They just run more plans. Plans and back.
Yeah, the 20 gallery.
Okay, good.
Yeah,
How
because
much
I
did you
think
say?
it was a lot, and yeah, her models are going a lot.
Even with
Because
the
I just
customized
started doing ours
things.
in the semester.
Oh, okay, perfect.
At the end of 2021, to like figure out how to even model it. Yeah, it's a lot.
Good.
She gave me a bunch of different
How long
references and
will it
everything too.
take to be ready?
No, I'm done.
Okay, yeah, I'll probably ship it to my parents' house then because I'll just be moving sometime. Yes. Yep. That's fine. Yeah. Discover 6011-0057-9256-6567.
Nice.
Yes, that's a money, that's totally all right. That would be.
Yeah.
Okay.
Oh, that was better than the store.
Huh?
It's optics that
Yeah.
see it. And then air takes
Yeah,
it out.
ponder. No, I
You do that, you do a shower.
Sure.
Yeah, Johnny Shockley brought one to the Boston Seafood Show 5 or 6 years ago.
What you doing?
Yeah.
Eric and Alyssa, neither of you look at your emails right
We
now.
were looking at that.
I think we can look later. I don't think it's
Nope, he said look now.
Separate.
Okay.
I can't get my email. Is it the same email?
I am assuming. Let's hope everyone can see it because everyone's gonna see it.
Don't put it up on the board.
Okay. Stop sharing. And no, everyone can't see my email. Okay. It's just the Don Davis thing.
Is this visual analysis thing?
Yeah, it's not. It's exactly what he had in the chat. Okay, yeah, this is.
Okay, he just said look at your email. I don't think he realized we saw the chat.
Yeah, I think he was just sending like the link and stuff in the
Yeah,
email.
that's fine. We'll get the word out.
Okay.
Alexis said, put it in my list of things to. Oh, okay.
Yeah, this is should be still recording. Let me check. Yeah, we're recording. So
So you're gone.
yeah, I figured at that point we should probably record. Thank you.
Thank you for coming. Wish you could be here for the next 2 hours. Well, you have to do things like that.
Okay, okay. Sounds good. I feel like we'll probably get things wrapped up today, but
Tom's main argument that I'll stay away from the family. I think I would suggest that we'll see how you
I would agree. Yeah, it's this whole thing. All our breaks are being recorded too. So. Yeah. Yeah. I totally meant to stop it during the breaks, but at this point, it's a little late to do that.
I think I'm going to sit up here, sort of stand up there and let you sit there and
Yeah.
coordinate things.
Sounds good. I mean, you're just thinking we might have to go back and reference presentations or something?
Might.
Okay.
You want to see what we can do with the stock synthesis and.
Oh, yes, you were gonna talk. You're up next. Sorry, I forgot about that. Yeah, you're definitely up next. Yeah. In fact, is everybody back? Okay. Warm me up.
I'm cold too.
Oh, and he's on the phone.
Well, Alyssa, why don't you tell everybody, what time is it there?
We have 2 minutes.
Okay.
Or
No, wait for the bell, because we said we would be.
so to be able to show it to everyone on Zoom, we'd have to have Zoom open on yours, or is it possible that you can send me what you have?
It's the internet will let me do that.
You just a memory stick?
Yeah,
I don't know if you looked at that email.
I did, yeah.
I have a USB too.
Oh, okay. I don't know if he needs, I have one of the dongle things.
We're gonna vote on staying late.
Yeah, everybody gets one vote.
Just one. Did the IAP get two? Wasn't there some rule about that years ago?
Dan's got a few things to cover that I have forgotten that we promised him.
No.
And then we'll bring up.
I already changed my plane. But the vote goes right.
You're optimistic.
We couldn't fly in at any kind of reasonable price, so we had to come into Hartford.
Really?
Yeah.
Providence?
Oh, Hartford was several $100s less.
Yeah.
It always is.
A lot of money.
Yeah.
It always is. That's why I-
Well, but speaking of that,
Still $700.
you know, message,
Yeah,
you gotta save a lot of money by staying here. going
I know,
to
but
Indiana.
we stayed over there because we thought we were gonna be able
That
to.
place got no rating. So did we canceled our rooms.
Well, you know.
Fairfield, yeah.
Thinking rubber.
Oh,
no, no,
destroyed.
Oh, yeah, well, that's okay. Take it to the board.
And you know that sort of obnoxious lady bartender that they
Yeah.
had?
Yeah.
She's still there.
She's still there. I think she's still in the business when it changes hands.
Yeah, right.
Like, And very. She did, well, she couldn't.
Not that guy, that bartender guy.
Yeah.
It's literally wouldn't wait.
Yeah.
Sitting down there.
I tried to on. Like one of the.
We went down to the quarter deck last night, and you know, it was just good at all.
So she was transparent.
Good restaurant.
Something more.
Well, it is a good bar.
Oh, yeah, yeah. What? Oh, let's, is Dan back there?
Right there.
So Dan, you're on.
Well, we're trying to figure out how to get it on here because it needs to be on the Zoom computer. So everyone on Zoom can see it.
Is it a- oh,
He- Yeah, he's figuring out how to.
Well, not now. Yeah, I was just gonna go by, Sandy, if the plant's working on getting us on the export list for Europe now that the EU shellfish ban has been lifted. And we can only export out of Massachusetts right
When
now.
you record a Zoom, does it like give you a script?
And
you
she
know?
sent me an email, she's got it done, so I'm
Because
gonna-
that'd be nice to use for notes, even though it'll have a lot of like. Just me talking right now.
She, started
I'm pretty sure
all
it
our
does.
PRC stuff and, she used to be like John's secretary, and now she's got more of a managerial role.
She focuses on the hymns and then once she gets it off, it's
Oh,
all
sorry,
the
board.
entirety is lost. Yep. It does take her longer. Yeah.
So
I just-
email that's in it.
Alyssa Leclaire at usm.edu. ALYSSA
Yeah.
dot LECLAIRE at USM. Yep.
Yeah, I'm just gonna go in.
Yeah, well, Claire has an E on the.
Yes, it does. As long as it gets here, that's all that matters. I'm sure I'm on. Well, yeah, if I'm on Zoom, I'm on the one.
Yeah, I put a midnight last night.
James is the MEGSA president.
wonder what happened to them all. If you're even right on that.
But she didn't send an email to Alyssa. I'm sure she.
Yeah, I would hope so.
Oops. This one has buttons, apparently. What did I do with it? Oh, yeah. Perfect. Oh. It's not the one I'm gonna start with.
Here, I think we might have to open image one again.
Okay.
Here, I'll just go to. Sorry, I have a zillion things pulled up. This is first
Okay,
image you want to
that'll
start with?
work, yeah.
Okay.
All right, so this is by way of just showing some of the flexibility that's currently built into stock synthesis. And the picture you're looking at is from a Red Drum review, and I'm using the pictures without permission, so don't tell them that I did this. It's a fish that grows for a long time. It lives for a long time, and they don't catch big ones very well. So they kind of don't have they don't have a good description of the asymptotic growth, assuming that it does ever stop growing. So what you're looking at are residuals from a fit with a standard von Bertalanffy growth curve. And you can see that the model line is above most of the data on the left here and below most of the data on the right, which should be a familiar state if you paid attention today during the ocean quahog growth discussion. And so this same thing for two different stocks. Next one. Cool. Okay. So this is a fit using the age varying K in the von Bertalanffy fit. So if you look closely, you can see that it doesn't, especially in this lower picture, there's not a pronounced asymptote to this fit. So they're still growing even at the very end of the data line. So that's a capability that SS has. And if you look at the residuals from that, get this one. So that's a much better fit.
And that's just by, so you basically either declaring a new K every so often, or you're telling the model to declare a new K every so often.
Yep. So yeah, you can either have it attempt to estimate it, which I would guess would be hard given that we don't have very many ages for ocean quahogs, or we can do something with our growth increments outside of SS, decide on a best shape, and then attempt to get SS into that shape using this technique, which would be what I would prefer. I don't think SS has a way to leverage growth increments, at least I'm not aware of it.
Calvin thought, yes, no, change.
Yeah. That's all I had for that.
Okay. So discussion time, folks. Time for me to ask questions and for the audience to answer them. Okay. So we'll start with number 7 here. The question is, what have we heard so far that would cause us to worry about the length-based model based on the variability of numbers at age per length class? Go for it, Dan.
So just point of clarity, the model is not actually length-based. It only uses only length data.
And so the model uses only length data, but it's not length-based. I'm repeating Dan's comment.
So the machinery underpinning the population dynamics of the model is the time step is a year, and the organism ages in the. So it's an age-based model. It's just that we don't have age data to put in there until now. That is definitely a problem. The fact that any given 1 centimeter length bin can hold hundreds of ages is not great. And what SS currently does is, because it has no way to know, we've gone ahead and told it that the growth curve has huge uncertainty. That's the best thing we could do given the information that we had going in. And because it has no information on growth, really, other than anything can do anything, just can't get smaller. And it has a bunch of lengths, but no ages. It knows nothing about the differences in recruitment that could have happened over time. So what it does is it puts all the recruitment into 1 year, because that's the most parsimonious solution. Every other year gets low recruitment, and you get a pretty weird looking distribution of ages underneath the model. I'm not sure that it makes a huge difference to the outcome, whether if we knew more about ages, we would still probably see a population that's lightly fished and, close to its virgin level. But we would have a much better understanding of when recruitment might have happened in the past. And we would probably have a better chance at trying to estimate a growth curve, even though I don't think we're there yet. And we would probably have a more precise estimate of the abundance of the stock. I guess I would argue that none of those things are super important to where the rubber meets the road and the quota happens. But
well, but are they important to? I would have. I don't find them interrupted. So
no, I'm pretty much done. I doubt that I think adding age is a very good idea, and I think what these guys have shown supports that. I think it would be easy to do. And I should say, Eric Robillard has taken on the aging from here. So he said, bring me shells next time you guys go out and survey quahogs, and we'll age them. I think he's going to be maybe unhappy if we bring in too many, but.
Does he use the same method?
Yeah, he's got to.
Yeah.
I shouldn't probably promise too much on that front, because we're at this interesting point at the center where we don't really port sample very much anymore because we're out of money for that program. So they're getting way less stuff from the fish world than they used to. So they have capacity. And I said, hey, we got Quahogs. And Eric said, let's do it. So he's going to try a few, see how long it takes, and then he's going to be able to do some number of the ages of the shells that we bring in. But maybe we can use your techniques for reducing the total sample. I'll probably end up bringing in like 1,200 or so ages per area. And we'll see how far that goes. But anyway, whatever he does, we will add to the model. And that will give us information that we don't currently have on recruitment and growth, and help with selectivity, and probably reduce the uncertainty that comes out on the other end. So,
two questions. What you just alluded to, the uncertainty in the order. We're still talking about, going back to the debate we've had in the last several sessions, it's not a debate because, you know, there's only one side of it. That basically one, which is we're not going with absolute numbers, we're going with trends and ratios. So is this going to affect the reliability or remove uncertainty from the trend ratio approach that you've been using with SO3?
This type of data is the kind of thing that would help move you in the direction of being able to say something about absolute biomass. But
let me just say that I keep bringing this point up because we're not in compliance with Magnuson. Magnuson requires the council to do, and to have a number, have numbers to do these quotas, and really, that's why that's a concern. So if we get further in that direction, that'd be great. But if it removes some of the uncertainty from the trends and ratios, that's great too. There would be some effect from all this work.
yeah, the inherent problem is that there isn't a lot of fishing effort on this stock. And I wouldn't stand up here and advocate like go fish 10 times harder. But if that did happen and we can see a response in the indices of abundance that we use, then we would know how many there were. But since the fishing right now doesn't seem to have any effect on abundance, as far as we can measure it, there's no way to know exactly how many. There's got to be enough for that to be true, but there could be this many or this many or this many. I don't either. And it probably, it's right now it's working, which, as far as the industry seems okay with it and the stock seems okay with it. So why change it?
And my second question is, would this work be something that you can use to address what seems to be the continuing reservations by some on the SSC about recruitment?
Absolutely. That we don't have any information on it right now because we don't have any ages. And once you have some ages, and that's a nice thing about Quahogs, which we haven't talked about yet, is that you can observe these cohorts for like 200 years, right? So information on recruitment has a long half-life. If we go out and sample right now, we can get information on recruitment back to 1800. And if we miss a year and wait and sample in 20 years, we still get pretty much the same information. So the more years you get ages, the more you can backfill that recruitment story. Even if you don't get a fully adequate age sample in 1 year, if you sample it for 25 years, retrospectively, you can do a really good job.
And that is an important point because, things change so slowly. getting samples in 2 consecutive years is almost like a replica.
Yeah, with so little F and so little M, then there's the same information is there from year to year. So even if you don't do a great job with either spatial or sample size coverage in 1 year, you have some more chances.
Okay.
I'll go sit down.
Anything else about number 7, or shall I go on to the next really important question? I only bring this one up because I really wanted to ask Dan this. Right now, we don't really have any good information on maturity. And we can take a decent guess, but it's just a guess. Do we need it? I mean, getting it means going to a different kind of dredge and the whole thing. I mean, it's not like you can just pick animals out of the dredge from the pursuit the way it operates. I mean, we'd have to do something different. Ogive.
Hey, guys, you're jargon.
Whoa, easy there. Okay, so my answer to that one is that I don't think it's going to matter very much. We currently have we're using a maturity curve that says that they're 50% mature at 5 centimeters, which was the best information we had at the time, and nothing I saw was different than that. But the reason I don't think it matters is that even if you're wrong by a few years of age or a couple of centimeters of growth, who cares? Because they have like another 200 years to be mature and reproduce. So it's not going to change the estimates of spawning stock biomass because there's so much biomass out there that's older than mature, and it's probably not going to change the estimates of reproductive capacity or productivity or whatever else for the same reason. So
Can I ask?
Yeah.
So how confident are you in what that original estimate is? The original derivation? Was it a study in the 80s, 90s, something?
It's basically information from Iceland.
Oh, from Iceland. Okay.
I remember Roger doing a little bit of work on that too, and I don't think he found anything that.
He didn't find anything, I don't think, remarkably different, but I don't think the work was, I mean, it hasn't been thoroughly analyzed. Many years ago, I did a literature search on bivalves to look at whether or not there was a relationship between size and at maturity and maximum size. And it's quite variable. But the majority of bivalves fall within a sort of a 30 to 60% range. And this 50 millimeters would fall within that range. So it would be consistent with the bulk of bivalves. And the only reason why I would have qualms about that is that might be the only thing about Arctica that's consistent with all the other bivalves. So who knows?
Way out of character.
Yeah, right. But you could make this argument that if you don't know what the maturity is, taking 50% of maximum size is a pretty good guess. And which is what I did in that paper, because I was doing something for all bivalves. And 50%, some of them get up to about 110 millimeters. You don't find them much bigger than that most of the time. That's about 55 millimeters. So, in that range, it's a reasonable guess.
And it's just the simple fact that they are mature for an additional 100 and whatever years after that, on average.
So you said centimeters and he said millimeters. So we're talking.
Well, it's 5
centimeters, 50 millimeters.
I mean, one of the things that you have from Kathleen's data, which you will have from Jill's, is the number of years it takes to get up to that size. And it's a relatively small fraction of the total age. So I think, you had maybe 15 or 20 years, something like that. The Iceland case, if I recall right, it's 50 or 60 years. But that's much, much colder water and they grow a lot slower. So, back down here, I mean, we're really talking about 2 decades in order to mature, probably. And we do have good data. If we believe the 52 millimeter number, we do have good data now on how long it takes them to get there.
Yeah, so I do see the big changes that I see in the assessment, and we're doing a Quahog assessment not too long from now. We have to go out and survey for them again, which is going to happen in 2024, 2025, something like that. And is that I'll add whatever ages we have for sure. And then I think we should go through the exercise of getting a better growth curve in there. And I think both those things are going to help with the uncertainty and probably not change the end result very much, but make a better assessment. Because right now it's kind of a silly one.
Which gets us right into 9. And so best formulation for a growth curve, I think that's solved. The issue would be, well, I have this written in several ways, so I may as well look at 9 and 10 both. The first question about growth curves is, how do we handle the fact that the growth rates have changed over the last 200 years, and there are animals in the population that have those different growth rates? We're going to, they will be aged. They will be generating age at length. And the animals born earlier will be smaller for a given length because originally they grew slower, right? So in my mind, that's a conundrum about how you do something about that. And the other piece of it is, do we need to worry about males and females?
I'll take what I consider the easy one first in that, which is the males and females thing. I don't honestly know what we could do in the assessment because we don't have any way to tell what's male and what's a female on the boat. And unless we develop that capacity, we're going to have to ignore that. I mean, there's tons of machinery in stock synthesis to handle sex specific assessments, but we don't have the information.
So I thought a lot about the sex differences. Kathleen has made a strong argument that the integrity of the age length piece is not a function of sex. If you have an adequate data set, the population number relationship is just as good as the male relationship or female relationship. She's also shown, and Jill has shown, that the actual age frequencies for the two sexes is effectively the same. One site, at the New Jersey one's a little bit off. The other 3 are dead on. So the assumption can be, I think, across the stock, the age frequency of the female is likely to be just as good. My concern is that the actual numbers of individuals that you need to age in order to get a certain level of certainty about the age frequency is, I think, going to be lower if you only work on one sex. And to me, that's the point, because Eric Robillard's sitting over there and he wants to know, can I get away with 200 animals or do I have to go to 400? And that a lot of that uncertainty is associated with the variability of age in size classes. And that variability goes up a lot if you put the males and females together. So that would be my argument would be, can I afford to, I mean, almost financially, can I afford to not sex them on the boat? In which case I'm now, paying Peter instead of Paul because I now have to age more animals in the lab. I think that's the way it's going to come out personally. That's the question.
Yeah, I mean, I understand. I think you made a good argument for detecting differences between the distributions of age frequencies, but the stock assessment doesn't, that's not what it needs necessarily to do the things that it needs to do. I mean, it can take any amount of information and that will help it to, for example, pin down differential recruitment in past years. Now, obviously it would do it better if it had more information, but some information is better than no information. Estimation of growth is another thing that this kind of data would be used for. I have no way of, I'm not smart enough to tell you how much we need to have to do that. I don't think we're going to have enough. I think we're going to have to do it outside the model. But
so the thing I'm sorry, go ahead.
Oh, no, I was just going to say, but I think it gets into the same sort of situation we've dealt with in the summer flounder, where there's a desire to move towards sort of the sex-specific approach, but you need all of the sex-specific pieces going forward, but also backwards in time as well, because you're going to be putting in all that historical data, and it creates a lot of challenges because you need sex-specific growth curves. You need to figure out sex-specific mortality, and even if you age a component of them on the surveys, you don't know if that is different than the ratios of sexes being killed by the fishery. So then you need sex there too to really tease out. So without all of those threads to put together, because otherwise you have to make assumptions about all those other pieces, and that almost seems messier than in some cases than just putting the data all together.
Yeah, I don't think it's quite that bad because the nice thing about ocean quahogs is they live so long that actually the sex ratio at age and size. If you have a sufficient age at length data set, you essentially know those parameters for the last 200 years. So you don't need to, so I think you get over the problem about various sex ratios over time, effectively immediately. The other thing is they're actually well-behaved locally, at least, with respect to the ratio at size. And we know the size frequency being caught by the dredges because that's something that you have data on. And so what Kathleen showed is that you can take the data from the age at length information and fairly accurately estimate how many males and females are being caught. I don't think there's any hindrance there. The only concern that you have there, which might be a big concern, is that that relationship of sex ratio with length is different for Long Island and Georges Bank. And it might be different from New Jersey. I don't know if you showed that, and maybe you did and I missed it, but you have the information. The ratio, the sex ratio with length, Kathleen had those bar plots. Right, but we do have the information, we just haven't presented it. So we can find out whether or not 3 of the 4 are similar and the 4th one's out, or they're all different. But they could all be different, in which case you'd have to do some sort of I don't know, either divide the stock up into pieces or do some sort of weighted average based on where the landings are coming from, or something like that.
Yeah.
But I don't think this is a big hump to get over. And I think this is really fairly straightforward.
Well, each time you subdivide your population, you double the number of parameters that you need to estimate. So you can chunk it up by sex, and then you can chunk it up by area after that. This is the important part. You supported me.
Yeah.
Anyway, the Quahog model right now, we're estimating almost nothing. I mean, it's honestly like it's not much of an assessment. You know, we estimate just a few parameters, some survey cues and initial recruitment, and that's about it. So I think just adding a couple data points in this new category isn't going to be enough to give us the ability to estimate a bunch of interesting things based on sex and spatial differences, at least in the short term. But that's not to say that's not something we should shoot for. So, I mean, it would be really great if we had a way to determine sex efficiently. You know, if there was some structure that we could look at that we didn't need a microscope in the inside of the clam to see.
Can't do that.
That would be nice, but the fact is that we only cut a few clams on the boat because it's only the ones that we do the meat weights for, and we save the shell from that animal, and that's what's going to get aged. So if we had to cut, it's a trade-off, right? If you spend time cutting open every clam and looking at them in a microscope to get a sex ratio for every toe, that means less toes you're able to do. So then you got to decide what's more valuable, the abundance estimate from, you know, a more robust data set per strata, or the sex ratio on each toe.
So, I mean, if you treated it a little bit like age, and you just every one that you aged, you had the sex, you would accumulate sex data at the same rate you're accumulating age data, and it would be distributed across the lengths because you're going to be choosing those things across the lengths. So you're kind of doing the only additional thing is you sex them by smear slide. Well, if you got to open up the thing to weigh the meat anyway, you just take a thing, put it on the slide, put it under a microscope, and it's literally five seconds. I mean, we sexed 1,500 ocean quahogs in about 2 days on the pursuit, with one person doing the smear slides. So it's not like you got to use histology or anything. You just look at it. It's either eggs or it's sperm, and it's right there. I mean, you do have to have a microscope set up in your van.
Yep.
You don't even have to change the slide. You just wipe the slide off, use it again. So I think with a little bit of extra effort, you could have sex for each of the animals that's aged. So the real question is that a little bit of extra effort useful enough to go to the survey branch and say, I want you to sex the animals that are aged?
Mm-hmm. Yeah, which yeah, we're gonna have to have our ducks in a row if we're gonna make that request.
right.
They were already complaining about every little new thing that gets loaded onto their
Well, can I ask a
beat down
layman's
shoulders.
question about
Yeah.
that? I mean, we provide people for the survey, right?
Well, we
Have in the
have in
past.
the past, yeah.
And is there any way that we could take that on? As simplest and say, okay, here's your 2 feet of countertop and your microscope, and we got 3 people shucking clams and 1 person operating the slot.
Yeah, I mean, it would help to have, I'm not sure anyone we have is comfortable being the expert at doing that right now. So it might be good to have, you know, somebody on there to train us and to show us how to do it. But I think we need to do some analysis before we make this request, because we need to make sure we want to go in this direction.
Well, I hate to be the financial guy here, but we've spent hundreds of thousands of dollars doing this. And our mantra is, you know, is to give us our fishery the best assessment that we possibly can. Take out any any confidence, any issues with confidence. So I mean, if we have traveled down this road and it doesn't really apply to anything, it'll have a great deal of influence on our future research. Basically.
Well, specifically, I'm talking about the sex issue only.
Yeah.
I don't know what to say about that. I am not really sure that asking the model to estimate an entire new set of twice as many parameters as it's currently doing and having trouble doing it is going to reduce uncertainty in any way. It might make the model less certain. I don't know.
So the other issue, because I want to get back around to what Dan just said, because I think a question toward the end of this meeting has to do with how we evaluate whether or not certain pieces of information are going to improve or not improve the model. But the growth rate over time issue, I think, is an enormous problem, because the growth rates are easily double and they might be triple in Long Island. Don't know, and if Sarah's data are anything like what, if Jill's data are anything like Sarah's off of New Jersey, they're going to be more than double off of New Jersey for animals that are presently living in the stock and contributing numerically to it. So a single growth curve is a growth curve for one of those cohorts sitting there in the population, right? Now, the question is, what does this do? Because these animals never get to a growth equilibrium. It doesn't exist in the population. And it probably cannot ever exist. And it probably never has in the past existed. So they are always a problem this way.
So that is something that we probably can handle in the assessment. I don't know if you guys remember, but we are allowing for time varying growth in the surf clam assessment currently. So there is machinery in there to do it. We estimated in the surf clam case, but I don't think we would want to do that here. But we could take the information that you guys have provided. Again, those growth increments are great, and develop, maybe decade-long growth curves, and then just tell the model, this is how quahogs grow in each of the decades in the past. So that, I mean, we can absolutely do that and should do that. And then maybe, after we've collected ages for 3 or 4 survey cycles, we can try to estimate it. And, maybe we can make some inference about even what might happen in the future in projections. So all that stuff is doable.
Well, that would be my strong recommendation, that you go in that direction, because right now I feel pretty confident we have roughly a growth curve that was roughly characteristic of 1800 and possibly off of New Jersey. I can't remember where that came from now. But what it is, it's a really slow growth curve. And the majority in the population are now growing much faster than that.
Yeah.
So we have a growth curve that's really out of sync.
Okay, well, that's good. Good piece of information. I agree, we should do that. And it's kind of interesting because I think you can make a choice about how you apply it. Like you can either apply it to cohorts or you can let everything grow based on the decadal scale curve, which is probably more how it works in nature.
Yeah. Well, you're probably going to have to do that anyway, because getting enough animals in a cohort to get a good estimate of the growth curve would take an enormous number of ages.
Right.
I mean, that's
Yeah, that's why I think the increments are.
the blocks of time idea.
Yeah.
is a good idea. Kathleen tried, for the data set she has, tried 10-year and 20-year blocks. And the 20-year blocks worked a lot better. You damped out a lot of the noise.
Okay.
So now, of course, if you had twice as many ages, you could probably go to 10-year blocks.
Right.
So part of that's how many animals do you have? But even if you went to 20-year blocks, you're talking about 5 blocks a century. So you're talking about 10 different growth curves just right there, right?
Yeah. Yeah, it's definitely a resource intensive assessment model. Takes 10 minutes to fit the 5 parameters I'm currently fitting.
This is the same question written twice. I knew I did that, so I'm going to get over it. And I've told you about 12, so we've got that.
Yeah, those are good.
Yeah. So, and we're going to get back to research observations. So what I'd like to do is go up here to the top. And now that we've heard all this information and we've discussed some of these points, the real question is, what are the priority issues from the standpoint of where we want to go on the assessment model? And to what extent do those generate science recommendations independent of the center? Because we know Eric Robillard is going to be aging things. We have some experts in aging, which I feel very confident he's going to take advantage of because he knows them already. So moving in that direction, in theory, doesn't take any more than CEMFAS making some of these people available for training sessions. Or you can always hire one. Yeah. Anyway, so that's a done deal. And I have actually, before we get to the assessment model, let me bring up one other thing. It's not on here, but I made myself a note to bring it up. I want to talk a little bit about survey design. Right now we're doing, and I'm sorry I'm blindsiding you with this, but I'm going to do it anyway. Right now we're doing 4 surf clam years and 2 ocean Quahog years. And we divided the world up into basically an inshore set of strata that are surf clam strata and an offshore set that are ocean Quahog strata. Some of them I think are sampled in both, right? Okay, so there's some overlap. We have from the pursuit cruise, the overlap of these 2 species is so much larger than it was when we retired the Delaware 2 that that's really unbelievable. And when we did our survey design work, which was like maybe 2016 or 2015, it's in that time frame. That was based, I think, on 1 pursuit cruise in the Delaware data set. So it's very likely in my mind that the stratum and strategy for the survey is actually now pretty much out of date. And we have too much overlap. We have animals in the wrong strata I mean, it's gotten very messy. And I personally think also we have much stronger information now about what we can expect from from climate change. Now, there's two important pieces of information with respect to the climate change thing. The first you've heard here today, and that's the data that Alyssa's put together, plus the information we've got from the pursuit that shows that these animals have routinely moved across the shelf. They've done it relatively fast, so the present rate is not unduly fast in comparison to things that have happened in the past. And the overlap right now with ocean quahogs, I think, sets up a real possibility that we're going to see a mortality event with respect to ocean quahogs. I think it has to be in the future sometime in the next decade or 2 decades. And it could easily be a Delmarva-like event when it happens. Okay. We know that the cold pool is degrading. It's degrading both on the inshore side and on the southern boundary. And we know that there are heat waves, a couple in particular since 2010, that strongly impacted the integrity of the cold pool on the southern and inshore boundary. There was a very bad one in 2016. And another one that was prior to that was a pretty record-setting one in 2012. So we can be prepared for one. So we have to worry about the fact that we can't go a long way without making sure our survey fits the problem that we have. Okay. The other thing is from Alyssa's data set, we know that we're going to have surf clams in catchable numbers, at least out to 60 meters. And we're very close to having that now off of Long Island on the northern side of Hudson Canyon. And that in the next 5 years, I guarantee you boats are going to be out there fishing. So, and of course the quahogs are out there right now. That's assuming, of course, you can sort out the surf clams and the quahogs,
mixed catch.
the mixed catch problem. So, that's one of the major things that worries me about the present status of the survey. And I wonder if it's not time to really start thinking again about what the future is with the survey, so it doesn't get so far out of whack that we end up really being, slapped down because we weren't ready for what almost certainly is going to happen.
Right.
The second thing, real quick, there's a project funded through a power company, actually, strangely enough, that is developing a forward projecting model, hydrodynamic, coupled hydrodynamic and surf clam model. The hydrodynamic model is set. I have heard from Daphne that the Rutgers people are pretty satisfied that this model is giving what they would claim to be reasonable projections out about 25 years. So you have the bottom temperatures. Now, Eric and a couple of other people are going to meet sometime in late May or early June to take the Cephas model, which is the surf clam fishery model, and set it up so we can move the clams consistent with the Rutgers hydrodynamic model. That's absolutely going to be online by the end of June, unless somebody dies or something, because we have to get that done. We have in the bank right now a very good description of the temperature requirements for that would generate fishable surf clam concentrations. So we can take that from the hydrodynamic model, we move the clams where those temperatures are. We should be in the process of being able to do projections out for the next 25 years about surf clams. Those two things, and that would be a piece of information that might inform survey plan. So one of the things I would recommend, and I'm open for discussion, I think it's time to get a survey group back together and really start worrying about how we're going to deal with this climate change issue, because it's certainly not going to go away.
So I agree with you that the survey strata need a close look. And one thing that I've always thought was nicely built into the current design is that our Quahog strata, as we say, are offshore of our surf clam strata. And so, and we know where they overlap and where they don't. And so if we go out and survey quahogs in 2024 or 2025, and we end up catching a lot of surf clams in strata that aren't supposed to have them in it, that's going to be a very strong indicator that it's time to redo the survey strata design. There is a little bit of cost to doing it too quickly. I don't think it's good to, like, you could presumably redo the strata every year. But it's not even that big of a problem statistically. I think they do that for scallops in Canada. But it is, to me, it's nice to be able to see. I kind of like to have the strata sampled where you're watching the progress of the surf clams go offshore. We wouldn't really know that they weren't in an area unless we go there and test it. So it's nice to have the same setup, at least for 1 or 2 cycles. But we had originally intended a decade before we revisited. But if we need to redo it after we do the Quahog one once, then we probably should do that. So I think I agree with you.
And that would be probably 2024.
Yeah, so this summer is Surf Clam South, 2023 is Surf Clam North, 2024 is Quahog South, 2025 is Quahog North.
2024 would be the data set that would make you make a decision one way or another.
Yep. So we would, after 2024, we could look at the data and say, hey, this is a problem, or maybe we have another couple of years to wait.
Well, we can put that in the record, and some of us may still be working in 2024. Okay, so then the last item on the agenda, which is kind of the big item, is can we make a list from all of this about what we might do to improve the assessment model? Are all these things that Dan needs to do, or are there things that we should do? Can we at least map out some kind of a strategy?
Well, I think if aging is going to continue to be a process, I think it would be a good project for SIMPAS to take the initial steps on at least exploring the optics that might be available. I mean, not to say that we're going to buy NIMS optic equipment, but we can certainly do research. We can work with the IUCRC. We can give them a project, to see what we have done and see what we can come up with. I think that's a reasonable something for us to look at in the short term.
From the person in their perspective, the people who ate all the time, like, that would be extremely helpful.
Well, and if the aging actually helps the assessment and it's going to be turned over to the lab, I mean, how much personnel time you guys had to do what they've been doing, as an educational process. So I'm afraid that if it is important, it might get washed out because it's onerous. It's time consuming. Time is money. And federal government finds a way to spend money other ways
Those results.
I mean, I think Robillard is looking at one full-time person if he's going to go into this. I don't see how you cannot, I don't know how you can have less than one technician.
Yeah, I think he's aware of that. I don't know if it's still on. I think he understands it's a big lift. But I mean, again, I would just point out that any ages we get are better than what we have. So even if we sample it inadequately every year, it's over time, it's still going to help a lot.
So one thought I was going to ask, I mean, we've talked about the growth curve changes that might be put in. We've discussed whether or not things would improve if we put sex specificity in it. Maybe it would and maybe it wouldn't, but we don't know. We might be worried about how uncertain we are about the age frequency based on the number of individuals that are being aged. There are a whole variety of things like that. Is this something that Dan's going to do all by himself? Or should we try and identify somebody to work on an improved surf clam model that could be associated with Dan in sort of a similar way, like we had Laura Solinger working with Dan on surf clams, and we've done some other internships. And I say this because I think Semphis could easily fund a postdoc if they wanted to. It's well within their budget if they chose to. If it was a PhD level graduate student, I'm very confident that we could get internship money out to put somebody up at the center for a while. So I don't want to like step on your toes, Dan, but I'm saying my point is I don't know how busy you are or what else you have to do, but it seems to me that we're at a point where there are a lot of questions that are modeling questions, and unless we solve some of those questions, we're not sure what else to do in the lab. As a modeler, that's what it appears to me to be.
Yeah. No, I'm not seeing any other obvious, nothing's crying out to me either for further lab work. I would say regarding a postdoc, a lot of this stuff I have to do anyway, but the sex specific thing is something that, I mean, I think it's going to take a lot of simulation stuff, some build up, some, if we had this kind of data, it would result in this kind of improvement to the stock assessment. So that might be some fertile ground for a postdoc project. And I'm not going to have time to I'm not going to be sitting here, running a bunch of, developing a bunch of fake sex data. And I don't think I have time to do that. So that would be one that would work.
So I have a question, because I know when we talked about different ways of breaking the model, we've been talking about that. But with the growth work, I mean, there were a couple of areas that were being looked at, and there were some differences among sex. Well, not just sex, but just the growth curves by region. So, I mean, I'm just wondering if going down the sex track is the right way to go versus going down sort of the
spatial,
spatial component, and how those might play out. Because I think that may be an interesting place to explore, especially if you're seeing some of those growth differences, doing some simulation work, because maybe, and right now we've got like the north-south, which is Georges Banks and south, for the way the data has been run for some of the models, but maybe there needs to be different breaks in there, or maybe there needs to be an inshore, offshore break.
So that's a really good point. I'm going to let you answer too, but I'm just going to make one real quickie. I thought about that a lot. And, the first big decision is, and I'll just use age frequency as an example. Do I take samples from across the stock, generate one age frequency for the stock and use that? And how much error is involved in doing that as opposed to, for example, taking an age frequency for New Jersey, one for Long Island, one for George's Bank, and putting that in, okay? And you could say the same for a number of the other pieces of information where there are very clear regional differences, which you could either average over across the stock or you could maintain regionally. I think that's an important research question, personally.
For me, with the warming temperatures and things shifting around, and things will continue to shift and move going forward. I think it's going to be an important one, not just for this stuff.
And you know, Alexis found pretty strong regional differences, but also very clear onshore, offshore differences. So, and that's for surf clams, but you know, somewhere along the line, basic physiology is going to play a role in very varying growth rates with respect to different temperatures and so on.
So those are good points, and I agree that it's important. And I would also just point out that this is both of surf clams and quahogs are great stocks for doing spatial stock assessment, because you know they don't move. You know where they came from when you catch them in the fishery or when you survey them. So there's probably more power there to do that kind of thing than in most fisheries. The problem historically has been that we don't sample well enough on the survey to get small area estimates. But that may have changed when we re-stratified everything, increased our sample density by quite a bit.
And with quahogs, you have the luxury again, which is what you pointed out. And I'm a total believer in this. If I take a sample of ocean quahogs 1 year, and then 4 years later, I take another sample, it's damn near the same sample. So I've doubled my numbers. For surf clams, you couldn't do it. The change would be too fast. But for ocean quahogs, there's enough temporal stability that you could build up a data set that was pretty profound just by recognizing that fact.
So with the sampling, now that you have the new survey data, it would be a good project for a student or someone to do the weights and say, do I have the power if I break it into 8 areas, or 6, or 4, or 3, or how does this perform, and how are my fits, and where's my, if somebody could take an actual, simulated set and actual set and kind of move through that, and then ask the question, where might it make sense to me to make a break?
Yeah.
So, and that seems like just an interesting.
I agree. So there's plenty to do for a postdoc, because that's another thing that I probably can't tackle.
I think the questions that are being asked here, just as for Tom and Guy, you could get away with a high-powered PhD level graduate student if it was someone that came out of the proper training lab as a master's. Okay.
I agree.
But if you were going to advertise for something, you would absolutely also advertise for a postdoc, because you would be advantaged if you could get the postdoc instead of the graduate student. But it's not a master's level project, and the cost is higher for that reason. It's not it's not going to cost you $200,000, but it's going to be more expensive. Not for Census. It's 10%.
Oh, okay.
Okay. Yeah. That's right. So it's really very, very efficient. And the intern,
Some of the universities scare me.
Yeah.
They'll be like 42%.
no, I know.
61%, and
That's what we did before 2013.
Yeah.
That was a big reason for census,
Yeah.
10%.
So it's sitting there at 10%. So, you know, if they put up $100,000 as an example, just a round number, 90,000 plus a little bit goes into science. And the less than 10,000 is 9,000 or something goes into indirect costs. So they get a lot of bang for their buck.
So can I change the subject slightly here?
Go for it.
I just wanted to mention to you guys in particular, just maybe so you can drum up some enthusiasm with your people. But Jessica and I put in a grant proposal to try to get some money together to work on some video analysis of clam catch, with the idea that we would get it some binocular cameras out filming the conveyor belt on the pursuit during our survey, and teach an AI how to tell the difference between a surf clam and a quahog, and then get us a count as they run up the belt, and then hopefully also a length measurement. I don't know if either of those things are doable, but they should be based on the
Who
technology.
did you put the proposal in?
It was it's an internal NOAA one. It's called FIS.
Is that for looking at the mixing issue?
That was the motivation behind thinking about this, because you know, we need some solution to the catch monitoring side of this. If we're going to allow mixed catches, that's a big problem for me, regardless of how it happens, because I don't see, like, you're not going to get a port sampler to come and dump a cage out on the dock and like count how many of each stock species is in there. That's just impossible.
Yeah, I mean, the only observation I would make about that, actually, I incorrect about this, but I think before we're too far down the road, spending a bunch of money on, you know, how do we account for mixed catches in the boat? We gotta get to a point that plants are willing to accept mixed catches on the other end, because right now,
Oh yeah.
we don't want that.
No, I know.
And so.
Right, and
right now, the
they.
solution is find a way to not bring in mixed catches.
But see, that's also a problem for me, because one of the ways that you could do that is by tossing all the quahogs out of your surf clam catch. And if I don't know about that, then I don't have an accurate measure of the catch.
Why would you not?
It's the mortality, bycatch mortality, discard mortality.
We have an estimate of that.
No, that's bottom.
Yeah.
But if they're being, the issue is, regardless of where they're being killed, we need to know where they're, so it doesn't, I mean, it kind of, if they're being thrown over and they're discard mortality, that would be good to know. If they're not being thrown over and they're just being run through cages and they're being discarded later, that would be good to know. Either way, we need to know the mortality.
Yeah,
on
right.
funds and so on.
I don't care that this is happening as long as I know about it, is my perspective as the assessment guy. I just need to have a count of how many are dead. It doesn't really matter how or where. It's just, well, where would be.
The 12%, I think it's 12% that we are using right now is an on bottom estimate for animals that are encumbered by the dredge but not caught.
Correct.
And the assumption is that anything that goes up in the boat goes into the plant. So there's effectively no discards. That's that problem. The other thing I was going to say is if you all don't get that and it's still deemed important, what I can't do is I can't fund anyone in a federal lab or anything.
No,
I can't do it.
Yeah.
But on the other hand, that is a project that would be eminently fundable by Census. We would just need to put our stuff on the boat and have some of our people involved in the cruise. So
It's certainly, none of the money needs to go to us. I mean, in fact, if we get the money, I'm just gonna hire somebody else to do it. It's gonna be a contracted job.
Right.
So I don't know how to do any of that stuff.
so, but if you don't get it, my point is that, and it is important and the board deems it important. It's eminently feasible for us to fund that and to put the people in place to do what otherwise you are going to do.
Okay, great.
So it's sitting there as an opportunity. But I can't pay you.
No.
I mean, I think
I can't pay Jessica.
Yeah, neither of us can get paid through the grant we wrote.
But
As it
I
is.
think it's a really good candidate, but the other sort of ancillary benefit that Dan's pointed out is as port sampling costs are going up and sampling is going down, if this technology is able to take lengths and do those measurements on board the vessels, whether it's the survey vessel or maybe in the future getting that length information and counts from the commercial fisheries as well, having all of that length information is going to be hugely valuable, and it'll free up time potentially for doing other work on the surveys. So you may not need to do as intensive length sampling to validate it once you've gone through a validation process with the technology. You may be able to just do a little sub-sampling and then be able to do other research work.
Like getting sexes on ocean cohogs.
You could. I mean, there are lots of other things that it could trade off for. So it's definitely a big advantage for the survey process as well and the research for.
And if you want to talk about a way to reduce uncertainty in the assessment, having more data from the catch, more commercial links would be a big help for the surf clam one.
Now, that's another thing. If we had some guidance about what the protocol was and dispersion of samples and the number desired and that sort of thing, so we could work out a budget, that would be another thing that we could fund. So we just need guidance of the specifics so I can put a budget together about the cost.
Okay.
I mean, we have done regional surveys before for other things. We know people in different ports who are academics who could be engaged to do this. So it's definitely a doable problem. You just need to get information in front of the board about what the specifics are.
Okay.
That's all.
When will your grant be awarded?
Well, all we've done so far is the pre-proposal, and I think we find out in June if they want a full proposal. And then we have to submit that at the end of the month. And then I think they probably let us know toward the end of the fiscal year for us. So this wouldn't be funded until,
So you couldn't get it out on the
it wouldn't
pursuit
be
this
out
year.
this year, it would be next year.
But you know what, I think we'd just be grateful to have you guys out and doing this.
Yeah, no kidding.
After 2 years of not getting survey data.
Yep.
Just getting everybody out and getting off without a hitch would probably be good for 2022 and then 2023,
Yeah.
probably not, that wouldn't be a bad way for the schedule to shake out.
Do we have any other subjects to talk about in virtual land or here? Do we have, Tom and Guy, enough guidance? Do I need to shake the rafters for more ideas? Where are we with everything?
So the one thing I did do while we were sitting here, I went back and just glanced at the SSC report for ocean quahogs back to 2017, just to see if there were any areas that they had highlighted that maybe were missed. So it might be good. I mean, it looked like a lot of those were related to age, to length. They did have the maturity, more information on maturity and fecundity. But also on their list, getting a better handle on, eggs produced at age or length, that kind of stuff. A lot of that early life history stuff that suggested a little icky. And then there were a few things in there, probably came from Wilbur related to modeling.
Is this the surf clam?
This is ocean
Oh,
quahog.
Chicago, okay.
Yeah, so they had a high priority, low priority list. I can forward the list to you, Eric. If, you know, if you guys
Yeah,
wanna
and
take
cut-
a look at it.
Copy it to Tom and Guy, and they probably got it, but just in case. The fecundity thing is an interesting problem. And I'm not sure in your assessment model to what extent it does anything. I mean, your assessment model is inventing recruitment, so you really don't care about fecundity, right?
No, it doesn't do anything except it. Well, there are outputs. There are fecundity-based outputs that I don't really do anything with. So if you knew more about it, you could have, I don't even remember what the term is now, but you can set it up so that, you know, fecundity is a function of weight or age or whatever. And then you can get like a, you know, eggs per
Yeah.
eggs
I'm-
per recruit kind of.
I mean, it's feasible to get fecundity information. It's a relatively expensive endeavor. And so that, you know, it would have to be something that would be really useful to really spend the money. Because, you know, you can get estimates of the stage of in the gametogenic cycle histologically. But what you really want is the number of eggs.
Yeah.
And that's an altogether a different animal to get
Right.
at.
Yeah, so when I think of that being useful is when you have a situation where fecundity has got some sort of nonlinear relationship to age, like you have a Pacific halibut or something where the biggest females are producing 8 times as many eggs as, you know, a fish that's only half as big, and that's when you start thinking about having a slot limit in the fishery or something like that, because you want to preserve the biggest, oldest fish. I don't think it's impractical in the clam fishery to think about a slot limit, so I don't know why we would.
And if it goes, if it's not a sort of linear relationship with biomass, I guarantee you it's going to go down and not up with the bigger animals. Which means that it's cheaper on the stock to catch the ones that are being caught. So, I mean, I've made this argument about fecundity a number of times, and we've done some fecundity work in the past, and I know what it takes to get egg counts. And it's just, you know, something like Quahogs, it'd be expensive.
Yeah.
So it'd have to be worth something.
I don't have, unless somebody teaches me something about it, I don't really have a reason to want that.
I sent it to you, Eric, and I sent it to Guy just to have, but, I mean, other than that, like, their first goal is survey performance, age and growth, spatial processes, and recruitment processes are all areas of need attention. I think it kind of sums it up, and then I have goals.
Yeah.
Around them.
Well, these guys have done a lot of work on those things, so I think we'll have, you know, as a clam concerned body, we'll have a lot to show the review committee next time we meet, which is great. Thanks mostly to you guys, since I didn't do any of it.
Anything else, folks? I mean, I hate for us to leave on time. Are we good? Uh-oh, well, and the chat is?
I'm assuming probably Roger. Yeah. Just the fecundity.
Yeah, we do have a steepness of 1.
Yep, that's right. That's not changing anytime soon.
So we won't meet tomorrow. Done. Thank you. Some of us are going to figure out a way to see Eric Robillard tomorrow. I think that's on the list.
Okay, good.
Alyssa, would you send Steve Cadron an email?
I don't have his email address.
Yes.
Yes, Cadron.